The Milky Way galaxy is a vast system that contains the Sun and billions of other stars. It appears from Earth as a faint glowing band of light in the night sky, but this visible portion represents only a small part of an enormous and complex structure. At its centre is the galactic core, a region hidden behind thick layers of gas and dust, where gravity, radiation and motion are far more intense than anywhere near our solar system. Travelling toward this centre would lead through a dense and active area of space where stars are formed, destroyed and influenced by the strong gravitational field of a supermassive black hole called Sagittarius A. How vast is our galaxy, and what does that immense scale mean for everything it contains? Before we dive in, share in the comments below where in the world you're watching from and what the time is for you now. Then sit back as we journey to the centre of the Milky Way galaxy. The Milky Way galaxy is the vast system that contains our solar system, along with hundreds of billions of other stars and planets. Its name comes from how it looks when seen from Earth, as a faint cloudy band of light stretching across the night sky. What we see as this hazy glow is actually the combined light of countless distant stars that are too far away to be seen separately by the human eye. The Milky Way is what astronomers call a barred spiral galaxy. This means it has several long curved arms of stars, gas and dust that wind outward from a central region, and a bright bar-shaped area made mostly of stars running through its middle. The full width of the Milky Way is estimated to be about 87,000 light-years across, while the spiral arms themselves are only about 1,000 light-years thick. However, computer simulations suggest that the invisible cloud of dark matter surrounding our galaxy might extend far beyond this, possibly reaching close to 2 million light-years in diameter. This dark matter halo may also contain some stars and faint structures that blend into the surrounding space. The Milky Way is not alone in space. It has several smaller satellite galaxies that orbit around it, such as the large and small Magellanic Clouds visible from the southern hemisphere. Together, these galaxies belong to a neighbourhood known as the Local Group, which is part of an even larger collection of galaxies called the Virgo supercluster. This in turn is one region within an enormous structure of galaxies known as the Laniakea supercluster, one of the largest known cosmic systems in the universe. Inside the Milky Way, scientists estimate there are between 100 billion and 400 billion stars, and possibly just as many planets. Our own solar system sits roughly 27,000 light-years away from the galactic centre, on the inner edge of a spiral arm called the Orion Arm. This is the region of the galaxy that contains our Sun, and most of the stars we see at night. Near the core of the Milky Way, within the central 10,000 light-years, stars are packed much more densely. There, they form a bright bulge and one or more bars that extend outward. At the very centre lies an extremely energetic source of radio waves known as Sagittarius A, which is actually a supermassive black hole containing about 4 million times the mass of our Sun. The oldest stars found in the Milky Way are almost as old as the universe itself, meaning they formed shortly after the first light appeared following the Big Bang's dark ages. The Milky Way has been observed and wondered about for thousands of years, but it was only in the year 1610 that Galileo Galilei used his telescope to see that the glowing band of light in the sky was made up of countless individual stars. For a long time afterward, most astronomers believed that the Milky Way contained every star in existence. It wasn't until the early 1920s that this idea changed. In the famous Great Debate of 1920, astronomers Harlow Shapley and Heber Doost Curtis argued about whether the Milky Way was the entire universe or just one of many galaxies. 3 years later, in 1923, Edwin Hubble proved that there were other galaxies beyond our own, forever changing our view of the universe. Throughout history, many cultures have created myths to explain the Milky Way's bright trail across the heavens. In ancient Babylonian stories, the Milky Way was said to have been made from the tail of a great sea dragon named Tiamat, after she was defeated by the god Marduk. The dragon's tail was placed in the sky to remind people of his victory. Greek mythology offered another explanation. It was said that the god Zeus placed his mortal son Heracles, known as Hercules in Roman mythology, at the breast of the goddess Hera while she slept, so the baby could drink her divine milk and gain immortality. When Hera awoke and realized she was feeding an unfamiliar child, she pushed him away and her milk spilled across the heavens, forming the shining band we call the Milky Way. In another version, The infant's strength startled Hera, and when she pulled him away in pain, her milk scattered through the night sky. The name Milky Way, used in Western languages, comes from this same idea of a milky path in the sky. The term itself is a translation of the Latin phrase Via Lactea, which came from the older Greek term galaxias kaiklos, meaning milky circle. From the Greek word galaxias also comes our modern word galaxy. The ancient Greeks considered the Milky Way one of 11 great circles in the heavens, alongside others like the zodiac, the horizon, the equator, and the polar circles. When viewed from a dark location, the Milky Way appears as a wide band of soft white light, about 30 degrees across, arching over the night sky. Every star visible to the naked eye is part of the Milky Way, but the term Milky Way usually refers to that concentrated band of light across the galactic plane. The glow we see comes from the combined light of distant stars and other material in the disk of our galaxy. In some areas, the Milky Way looks brighter, forming what astronomers call star clouds. The most prominent of these is the large Sagittarius star cloud, which is part of the central bulge of the galaxy. There are also dark patches where light seems to disappear. These are regions filled with dense clouds of interstellar dust that block the light from background stars. Cultures in the southern hemisphere, such as the Inca and Australian Aboriginal peoples, often saw these dark areas not as empty spaces, but as dark cloud constellations representing animals or spirits. The region of the sky hidden behind the Milky Way's dense disk is known as the zone of avoidance because it makes distant galaxies hard to see. Despite its size, the Milky Way has a fairly low surface brightness. This means that it can be hard to see from places with bright city lights or a full moon. To view it clearly, the sky must be quite dark, darker than about magnitude 20.2 per square arc second. It becomes visible when the faintest stars you can see are of magnitude 5 or better, and it reveals its finest details when stars of magnitude 6 can be seen. Because of light pollution, more than 1/3 of people on Earth can no longer see the Milky Way at all from where they live. But in rural areas, far from artificial lights, it still appears as a magnificent river of light stretching from horizon to horizon. From Earth, the Milky Way's band passes through about 30 constellations in the night sky. The brightest part lies in the direction of the constellation Sagittarius, which marks the centre of our galaxy. From there, the band curves around to the constellation Auriga, where it reaches the opposite side of the galactic plane and then loops all the way back to Sagittarius. This vast circle divides the night sky into two almost equal halves. The plane of the Milky Way is tilted at an angle of about 60 degrees, compared to the path the Sun takes through the sky, known as the ecliptic, and about 63 degrees relative to the celestial equator. Long before modern telescopes and space observatories existed, people were already trying to understand the pale, glowing band that stretches across the night sky, what we now call the Milky Way galaxy. The earliest explanations came from the great thinkers of ancient Greece. Around the years 384 to 322 before Christ, the philosopher Aristotle wrote about these ideas in his book Meteorologica. He explained that earlier Greek philosophers, such as Anaxagoras, who lived around 500 to 428 before Christ, and Democritus, who lived between 460 and 370 before Christ, believed that the Milky Way's faint light came from distant stars hidden behind the Earth's shadow. They suggested that these stars could not be seen individually because their glow was dimmed or blocked by sunlight, making them appear as a misty band. Aristotle, however, disagreed. He thought the Milky Way was not made of distant stars, but was actually part of the Earth's upper atmosphere, the same layer where he believed the stars themselves were located. According to him, this glowing band was formed by heat and fire from the stars that burned in the outermost part of the atmosphere. The light, he argued, did not fade because of its high position, and the milky colour came from the bending or refraction of light in the atmosphere. Several centuries later, new philosophers began to question Aristotle's idea. One of them was Olympiodorus the Younger, a philosopher of the Neoplatonist school who lived around the years 495 to 570 after Christ. He pointed out that if the Milky Way were truly part of the Earth's atmosphere, it should appear different depending on one's location or time of observation, and it should also show a shift in position, known as parallax. Since none of this happened, Olympiodorus argued that the Milky Way must be celestial, a real part of the heavens far beyond the moon. This idea would later influence Muslim astronomers who continued exploring the nature of the cosmos. By the 10th century, scientific understanding had moved much further east. The Persian scholar al-Biruni, who lived between the years 973 and 1048, wrote that the Milky Way was made up of countless fragments of the nature of nebulous stars. He was among the first to suggest that what looked like a smooth glowing cloud was actually made up of many tiny star-like points, too faint to be seen individually. A little over a century later in Muslim Spain, the Andalusian astronomer Avempace, who died in the year 1138, made similar observations. He claimed that the Milky Way was composed of many small stars that appeared blended together because of how light passed through the Earth's atmosphere. As evidence, he referred to his own observation of a close meeting of Jupiter and Mars in the year 1106 or 1107, noting how their combined brightness resembled the Milky Way's diffuse light. During the 13th century, the Persian astronomer Nasir al-Din al-Tusi, who lived from 1201 to 1274, described the Milky Way in his work Tadhkira. He wrote that it was made of an enormous number of small, tightly packed stars that appeared cloudy and milky because of their concentration and faintness. Around the same time, the Islamic scholar Ibn Qayyim al-Jawziyah, who lived from 1292 to 1350, agreed with this idea. He described the Milky Way as a myriad of tiny stars packed together in the sphere of the fixed stars. The first solid proof that the Milky Way truly consisted of countless stars came much later, in the year 1610. The Italian astronomer Galileo Galilei used one of the earliest telescopes to study the Milky Way, and discovered that it was filled with an immense number of faint stars. Through his telescope, what once looked like a hazy streak became a field of glittering points of light. Galileo, however, still believed that the Milky Way's glow was influenced by refraction in the Earth's atmosphere. A century and a half later, new ideas began to emerge. In the year 1755, the German philosopher Immanuel Kant wrote a treatise based on the earlier ideas of the English astronomer Thomas Wright. Kant suggested, correctly as we now know, that the Milky Way was a vast rotating collection of stars held together by gravity, much like the Sun's planets in the solar system, but on a far greater scale. According to this model, the stars formed a gigantic flattened disk, and from our position within that disk we would see it as a glowing band across the sky. Both Wright and Kant also proposed that some of the other misty patches, or nebulae seen in the night sky, were actually other galaxies, vast island universes like our own. This poetic term remained popular until the early 20th century. The first detailed attempt to map the shape of the Milky Way came in the year 1785. The British astronomer William Herschel carefully counted the number of stars visible in different parts of the sky and created a diagram of the galaxy's shape. His drawing placed the solar system near the centre of a roughly flattened structure, though we now know this was only partly accurate. By the middle of the 19th century, technological progress brought new discoveries. In the year 1845, Lord Rosse built a powerful telescope capable of distinguishing between elliptical and spiral nebulae. For the first time, he was able to identify individual points of light within some of these nebulae, supporting Kant's earlier theory that such objects were made up of stars and could be separate galaxies. At the start of the 20th century, astronomers began to study how stars moved through space. In the year 1904, the Dutch astronomer Jacobus Kapteyn discovered that stellar motions were not random, as once thought. He found that stars could be divided into two large groups moving in nearly opposite directions. His findings turned out to be the first evidence that the Milky Way itself was rotating, a discovery later confirmed by astronomers Bertil Lindblad and Jan Oort. In the year 1917, the American astronomer Heber Doost Curtis studied a nova, a sudden brightening of a star, that appeared within the Great Andromeda Nebula, also known as Messier Object 31. By comparing old photographic plates, he found 11 more novae in the same nebula. Curtis noticed that these novae were about 10 magnitudes fainter than those seen in the Milky Way, suggesting that Andromeda was much farther away. From this, he estimated its distance to be about 150,000 parsecs, and became convinced that the spiral nebulae were separate galaxies, not part of our own. In the year 1920, a famous event known as the Great Debate took place between Harlow Shapley and Heber Curtis. They argued about the size of the Milky Way, the nature of spiral nebulae, and the scale of the universe itself. Curtis supported the idea that Andromeda and similar objects were island universes far beyond the Milky Way. The debate was finally settled a few years later. In the early 1920s, the American astronomer Edwin Hubble, working with the giant 2.5-meter, 100-inch Hooker telescope at Mount Wilson Observatory, captured detailed photographs of several spiral nebulae. These images revealed that their outer parts were made up of individual stars. More importantly, Hubble identified a special kind of variable star known as a Cepheid, which allowed him to measure distances accurately. He found that the Andromeda Nebula was about 275,000 parsecs from the Sun, far too distant to be part of the Milky Way. This discovery forever changed our understanding of the universe, proving that the Milky Way is just one of countless galaxies scattered across the cosmos. The European Space Agency's spacecraft Gaia has been carrying out one of the most remarkable missions in modern astronomy. Its purpose is to carefully measure the distances to stars by tracking their parallax, which is the tiny shift in a star's apparent position as Earth moves around the Sun. Through this method, Gaia has been able to determine the positions and motions of about 1 billion stars, creating the most complete and detailed map of our galaxy ever made. The information gathered from Gaia has been called transformational because it has completely changed how astronomers understand the Milky Way. Before Gaia, by the late 20th century, scientists had managed to study only around 2 million stars. Now, thanks to Gaia, that number has grown to 2 billion, 1,000 times more precise and covering 100 times greater volume of space. This leap in data has provided a much clearer picture of the Milky Way's shape, structure, and movement. In the year 2020, scientists studying Gaia's results made a fascinating discovery. The entire Milky Way seems to be wobbling. This means that the galaxy is not perfectly stable in its motion. The wobble might be caused by several factors, perhaps because the galaxy's flat disk is slightly tilted compared to its outer halo, or because of matter that the Milky Way absorbed long ago from smaller galaxies, or possibly due to the gravitational pull of nearby satellite galaxies tugging on it. Then, in April of the year 2024, new maps created from Gaia's data also revealed valuable details about the magnetic fields that weave through our galaxy, offering clues about how interstellar gas and dust move and form new stars. Our Sun lies near the inner edge of a spiral arm of the Milky Way known as the Orion Arm. It sits within a region of space called the local fluff, which itself is part of a larger bubble of low-density gas known as the local bubble. The Sun's position falls between two major wave-like structures in the galaxy's neighbourhood, the Radcliffe Wave and the split linear structure, once known as the Gould Belt. Studies of stars orbiting the supermassive black hole at the centre of the Milky Way, known as Sagittarius A, have allowed scientists to estimate the Sun's distance from the galactic centre. According to one study led by Reinhard Genzel's team in 2016, that distance is around 27,140 light-years. Another study from the same year by Andrea Gheze's group found a slightly smaller figure, about 25,640 light-years. At present, the Sun is located roughly 5 to 30 parsecs, which equals about 16 to 98 light-years, above the central plane of the Milky Way's main disk. The distance from our local arm to the next one outward, called the Perseus Arm, is roughly 2,000 parsecs, or about 6,500 light-years. The Sun, along with the entire solar system, lies within a region of the galaxy thought to be especially favourable for life, often called the galactic habitable zone, where conditions are stable enough for planets like Earth to exist and evolve. Within a region of space centred on the Sun that extends 15 parsecs, about 49 light-years, astronomers have found around 208 stars that shine brighter than a certain level known as absolute magnitude 8.5. This gives a rough density of 1 bright star per 69 cubic parsecs, or roughly 1 per 2,360 cubic light-years. However, when fainter stars are included, the numbers rise dramatically. Within just 5 parsecs, or 16 light-years of the Sun, there are 64 known stars, not counting 4 brown dwarfs, giving a density of 1 star per 8 cubic parsecs, or about 1 per 284 cubic light-years. This clearly shows that faint stars are far more common than bright ones. Across the whole sky, there are only about 500 stars bright enough to be seen with the naked eye, brighter than apparent magnitude 4, Yet there are around 15.5 million stars that are visible to telescopes at brightness levels above apparent magnitude 14. The solar apex, or apex of the Sun's way, is the direction in which the Sun moves as it travels through the Milky Way. In general, this direction points toward the bright star Deneb, located in the constellation Cygnus. The Sun's motion lies roughly 90 degrees away from the direction of the galaxy's centre. The orbit of the Sun around the Milky Way is mostly elliptical, but it is not perfectly smooth. It is influenced by the spiral arms and by uneven concentrations of matter throughout the galaxy. The Sun also moves up and down through the galactic plane as it orbits, crossing this plane roughly 2 7/10 times during each complete circuit around the galaxy. This motion has been compared to a simple harmonic oscillation where the Sun bobs above and below the disk in a regular pattern. In the past, scientists thought these oscillations might line up with mass extinction events on Earth, but later research using data from carbon monoxide clouds found no real connection between the two. It takes the solar system about 240 million years to make one full orbit around the Milky Way, a period sometimes called a galactic year. Since the Sun formed about 4.5 billion years ago, it has completed roughly 18 to 20 orbits around the galactic centre. From the time the first humans appeared, the Sun has completed only about 1/1250th of a full orbit. The solar system moves around the galactic centre at an incredible speed of about 220 kilometers per second, which equals 490,000 miles per hour, or roughly 0.07% of the speed of light. Relative to the surrounding interstellar gas within the heliosphere, the Sun itself moves at about 84,000 kilometers per hour, or 52,000 miles per hour. At this pace, it takes approximately 1,400 years for the solar system to move 1 light year, and about 8 days to cover 1 astronomical unit, which is the average distance between Earth and the Sun. The solar system is currently travelling in the direction of the constellation Scorpius, which lies along the ecliptic path followed by the Sun and planets. Astronomers also divide the Milky Way into 4 galactic quadrants, sections like slices of a circle, based on a coordinate system that takes the Sun as the centre. From above the galaxy's north pole, the system defines 0 degrees as the line running from the Sun straight toward the galactic centre. The angle, called galactic longitude, increases counterclockwise as one looks down from the north of the Milky Way. From the southern side of the galaxy, the same longitude would increase clockwise instead. These quadrants are often referred to by order, such as the first galactic quadrant, the second galactic quadrant, and so on. This system helps astronomers map and locate stars, nebulae, and other objects throughout the galaxy with great precision. Through missions like Gaia and decades of careful observation, humanity has gained a far clearer sense of its position within the vast Milky Way. What was once only a faint band of light in the sky is now understood as an enormous and dynamic galaxy, one that our Sun and Earth are steadily moving through on a journey lasting hundreds of millions of years. The Milky Way is one of the 2 largest galaxies in a small cosmic neighbourhood known as the Local Group, the other being the Great Andromeda Galaxy. However, even though astronomers have studied our galaxy for centuries, its true size, especially the exact width of its galactic disk and how that relates to what is called its isophotal diameter, is still not completely understood. Most of the Milky Way's stars are believed to be packed within a region about 26 kiloparsecs wide, which equals roughly 80,000 light-years across. Beyond this enormous disk, the number of stars quickly falls to very few, much lower than what would be expected if the density of the inner regions simply continued to decrease smoothly outward. In other words, the outer edges of the Milky Way fade away much faster than its bright centre. Astronomers use several different ways to measure the size of a galaxy, and these methods often give slightly different answers. One of the most widely used techniques is known as the D25 standard. This method measures the point where the brightness of a galaxy, in blue light, with a wavelength of about 445 nanometers, drops to a certain level, 25 magnitudes per square arc second. This point is then used to define the visible edge of the galaxy. In 1997, an astronomer named Goodwin and his colleagues used this approach by studying a type of pulsating star called a Cepheid variable. They compared the distribution of these stars in 17 other spiral galaxies to those in the Milky Way. By modelling how bright these galaxies appeared, They estimated the Milky Way's isophotal diameter to be about 26.8 kiloparsecs, or roughly 87,400 light-years across, with an uncertainty of about 3,600 light-years. They assumed that the Milky Way's disk follows an exponential pattern, meaning that its brightness fades steadily with distance from the center. According to their model, the galaxy's central brightness was around 22.1 B magnitudes per square arc second, and its disk had a characteristic scale length of about 5 kiloparsecs, or 16,300 light-years. This makes the Milky Way noticeably smaller than the Andromeda Galaxy, whose isophotal diameter is larger, and also slightly smaller than the average size of many other spiral galaxies, which tend to have diameters of about 28 kiloparsecs, or 92,000 light-years. The researchers concluded that neither the Milky Way nor the Andromeda Galaxy are among the biggest spiral galaxies known. Contrary to older beliefs, they are actually average-sized galaxies, large and majestic, but not unusually so. To understand this scale in more familiar terms, if our entire solar system, extending out to Neptune, were shrunk down to the size of a US quarter coin, about 24 millimeters wide, then the Milky Way would stretch across roughly the full north to south length of the mainland United States. An older study from 1978 gave an even smaller estimate, suggesting that the Milky Way's diameter might be around 23 kiloparsecs, or about 75,000 light-years. In 2015, astronomers found something new and surprising: a faint, ring-like structure of stars known as the Triangulum Andromeda Ring, or Triand Ring. This massive ring appears to ripple above and below the flat plane of the Milky Way's disk. Together with another structure called the Monoceros Ring, it was thought that these might be the result of large-scale waves or oscillations in the galactic disk, wrapping all the way around the galaxy at a diameter of at least 50 kiloparsecs, or about 160,000 light-years. If true, this would mean that the Milky Way's stellar disk is far larger than previously believed, possibly extending twice as far as earlier estimates suggested. However, a newer study published in 2018 challenged this interpretation. It argued that these rings were not parts of the Milky Way's main disk, but rather clusters of stars that had been thrown out from it in the past. These stars, including a type known as RR Lyrae stars, were found to have speeds and motions more consistent with those of the galaxy's outer halo rather than its thin, rotating disk. Another study from the same year, 2018, provided further insight into how far the Milky Way's disk might truly reach. It found that some stars belonging to the galactic disk may lie as far as 26 to 31.5 kiloparsecs from the galactic center. That is between about 84,800 and 103,000 light-years away, and possibly even farther. This discovery showed that the Milky Way's disk does not end abruptly at about 13 to 20 kiloparsecs, or 40 to 70,000 light-years, as had long been assumed. Instead, there are many more stars extending into the outer regions, suggesting the galaxy's disk is far more extensive than once thought. Then, in 2020, researchers used advanced computer models to estimate the reach of the Milky Way's dark matter halo, the invisible cloud of mysterious matter that surrounds the visible galaxy and holds it together through gravity. They found that this halo likely extends out to about 292 kiloparsecs from the center, which is around 952,000 light-years. That means the entire dark matter halo of the Milky Way could span a diameter of about 584 kiloparsecs, or roughly 1,900,000 light-years across. Finally, the Milky Way's main stellar disk, where most of its bright stars, nebulae and spiral arms lie, is thought to be about 1.35 kiloparsecs thick, which equals around 4,000 light-years. Though thin compared to its vast width, this galactic plane is where nearly all of the activity of our galaxy takes place, from the birth of new stars to the swirling motion of countless systems orbiting the galactic center. The Milky Way galaxy is truly enormous, not only in size but also in mass. Astronomers estimate that its total mass is about 0.88 trillion times the mass of our Sun, using a galactic boundary that stretches roughly 200 kiloparsecs, or about 650,000 light-years from the center. However, this number is not fixed. The estimated mass of the Milky Way can change depending on what kind of data or method scientists use. At the lower end of the range, the Milky Way's mass might be around 580 billion solar masses, which would make it a bit lighter than the neighbouring Andromeda Galaxy. In the year 2009, astronomers using the Very Long Baseline Array measured the speeds of stars located at the farthest reaches of the Milky Way. These stars were moving at extraordinary speeds of about 254 kilometers per second, or around 570,000 miles per hour. Since the speed at which a star orbits depends on the total mass within its orbit, these high speeds suggested that the Milky Way might be heavier than earlier estimates indicated, possibly close in mass to the Andromeda Galaxy, at around 700 billion solar masses within a distance of 160,000 light-years from the galactic center. A year later, in 2010, another study looked at the motions of stars in the outer halo of the Milky Way and concluded that the mass contained within 80 kiloparsecs, or roughly 260,000 light-years, was again around 700 billion solar masses. By 2014, newer measurements estimated the total mass of the Milky Way to be about 850 billion solar masses, which would make it only about half as massive as the Andromeda Galaxy. Then, in 2019, astronomers proposed a larger figure, around 1.29 trillion solar masses, suggesting that the galaxy might be more massive than previously thought. However, not all of this mass comes from stars, planets, and gas that we can see. In fact, most of the Milky Way's mass appears to come from something invisible: dark matter. This mysterious substance does not emit, absorb, or reflect light, but it exerts a strong gravitational pull. Scientists believe that a massive halo of dark matter surrounds our galaxy, stretching far beyond the visible stars, possibly extending over 100 kiloparsecs from the galactic center. Models of the Milky Way suggest that the dark matter alone could have a mass of between 1 trillion and 1.5 trillion solar masses. Other studies conducted between 2013 and 2014 have given a much wider range, from as low as 800 billion solar masses to as high as 4.5 trillion solar masses. By comparison, all the stars in the Milky Way combined are estimated to have a total mass of only between 46 billion and 64 billion solar masses, a tiny fraction of the galaxy's overall mass. Beyond the stars, the Milky Way also contains vast amounts of interstellar gas made up of about 90% hydrogen and 10% helium by mass. About 2/3 of the hydrogen exists in its atomic form, while the remaining 1/3 is in the form of molecular hydrogen, where atoms are bonded together. The total mass of this gas is estimated to be between 10 and 15% of the total mass of all the stars in the galaxy. On top of that, there is also interstellar dust, which contributes about 1% of the total mass of the gas, adding yet another layer of complexity to the Milky Way's composition. In March of 2019, astronomers announced that the Milky Way's virial mass, that is the total mass including dark matter within a certain radius, was about 1.54 trillion solar masses within roughly 130,000 light-years from the center. This was more than twice as much as some earlier studies had suggested, and it implied that nearly 90% of the galaxy's total mass might be made up of dark matter. Yet, science is always evolving. In September of 2023, using data from the Gaia spacecraft, astronomers came to a very different conclusion. Their new calculations suggested that the Milky Way's virial mass might be only about 206 billion solar masses, just 1/10 of what earlier estimates proposed. The Milky Way, our home galaxy, is a vast and complex system filled with hundreds of billions of stars, planets, and other celestial objects. Astronomers estimate that it contains somewhere between 100 billion and 400 billion stars, and at least that many planets. Finding an exact number is nearly impossible because many of the faintest stars, those with very low mass, are extremely difficult to detect, especially when they are more than about 300 light-years away from the Sun. For comparison, our neighbouring galaxy, Andromeda, is even larger, holding an estimated 1 trillion stars. Within the Milky Way, scientists believe there may be about 10 billion white dwarfs, 1 billion neutron stars, and around 100 million stellar black holes. The space between all these stars is not empty. It is filled with a thin mixture of gas and dust called the interstellar medium. This material stretches across the galaxy, forming a wide disk that extends as far as the stars themselves. Its thickness varies greatly. The colder regions of gas are only a few hundred light-years thick, while the warmer ones can spread over thousands of light-years. Unlike a solid object, the Milky Way does not end suddenly. Instead, the number of stars gradually thins out as one moves farther from the galactic center. Beyond a distance of roughly 40,000 light-years from the centre, the population of stars drops rapidly. Surrounding this vast disk is a roughly spherical region known as the galactic halo, made up of older stars and globular clusters. This halo stretches even farther out, but its size is limited by the orbits of two nearby satellite galaxies, the Large and Small Magellanic Clouds, which pass within about 180,000 light-years of the Milky Way's centre. Objects beyond this distance are likely disturbed or pulled away by the gravity of these satellite galaxies. The overall brightness of the Milky Way, measured in terms of absolute visual magnitude, is about -20.9, a figure that shows how luminous our galaxy truly is when compared with others. Modern discoveries have revealed that planets are just as common as stars in our galaxy. Observations using methods such as gravitational microlensing and planetary transits suggest that almost every star in the Milky Way has at least one planet. That means there could be anywhere from 100 billion to 400 billion planets. A study in January of the year 2013, based on the Kepler Space Observatory's data from a system called Kepler 30y, supported this estimate. Another study from the same month suggested that there are at least 17 billion Earth-sized planets in the Milky Way. Later that same year, in November 2013, astronomers reported that as many as 40 billion Earth-sized planets could be orbiting within the habitable zones, the regions where liquid water might exist, of sun-like stars and red dwarfs. Around 11 billion of these planets may orbit stars similar to our Sun. The closest known exoplanet is believed to be only about 4.2 light-years away, circling the red dwarf Proxima Centauri, according to a study published in the year 2016. These smaller, Earth-like planets may actually outnumber the larger gas giants, but they are much harder to detect because of their small size. Scientists have also discovered comets beyond our solar system, known as exocomets, and they might be quite common in the Milky Way as well. More recently, in November 2020, researchers estimated that over 300 million potentially habitable planets could exist in our galaxy. Despite its enormous population of stars and planets, the Milky Way emits fewer neutrinos, tiny, nearly massless particles, than many other galaxies. This makes our galaxy something of a neutrino desert when compared to more active and energetic galaxies across the universe. Structurally, the Milky Way has a bar-shaped core made of stars, surrounded by a vast, slightly warped disk of gas, dust, and stars. Its overall structure is classified as an SBC-type spiral galaxy, meaning it has loosely wound spiral arms. The idea that our galaxy is a barred spiral rather than an ordinary spiral was first suggested by astronomers in the 1960s. This was confirmed decades later, in the year 2005, when the Spitzer Space Telescope revealed that the Milky Way's central bar is larger and more pronounced than previously thought. Our Sun is located about 25,000 to 28,000 light-years from the galactic centre. These estimates come from geometric calculations and measurements of specific astronomical objects that serve as distance markers. In the innermost region, within about 10,000 light-years of the centre, lies a dense concentration of mostly old stars forming a roughly spherical area called the bulge. Some astronomers believe the Milky Way does not have a traditional bulge, but rather a pseudo-bulge that developed as a result of the stretching and twisting of the central bar during the galaxy's history. At the very centre of the Milky Way is a powerful radio source known as Sagittarius A star. Observations of the movement of nearby stars and gas show that this region contains an extremely massive and compact object. The best explanation is that it is a supermassive black hole with a mass about 4 to 4.5 million times that of the Sun. This black hole is currently relatively quiet, feeding very slowly on surrounding material at a rate of only about 100,000th of a solar mass per year. Similar supermassive black holes are believed to exist at the centres of most galaxies in the universe. The exact structure of the Milky Way's central bar is still debated. Estimates of its half-length range from about 3,000 to 16,000 light-years, and it may be tilted at an angle of 10 to 50 degrees relative to the line between Earth and the galactic centre. Some researchers even propose that the Milky Way might have two bars, one nested inside the other. Around the bar lies a ring of gas known as the 5 kiloparsec ring, which contains much of the galaxy's molecular hydrogen and is a major site of star formation. If we could observe the Milky Way from the Andromeda Galaxy, this ring would appear as one of its brightest features. High-energy X-ray emissions have been detected coming from the region around the central bar, aligning with areas rich in massive young stars and extending along the so-called galactic ridge. Finally, in June of the year 2023, a team of astronomers led by Naoko Kurahashi-Nielsen announced that they had, for the first time, detected neutrinos coming from the galactic plane of the Milky Way. This groundbreaking discovery provided the first neutrino map of our galaxy, opening a new window into how it emits and interacts with some of the most elusive particles in the universe. Since the early years of the 1970s, scientists have been detecting mysterious bursts of high-energy light, known as gamma rays, coming from the general direction of the center of our galaxy. These gamma rays have a specific energy of 511 kilo-electron-volts, and they are produced when tiny particles of antimatter, positrons or anti-electrons, collide and destroy each other with their normal matter counterparts, electrons. In the year 2008, astronomers discovered that the sources of these gamma rays seem to be distributed in a pattern similar to that of low-mass X-ray binary systems. This finding suggested that these X-ray binaries, which are pairs of stars where one is often a neutron star or a black hole, might be producing positrons and electrons that drift through space before finally slowing down and annihilating each other. These important observations were made using satellites operated by both NASA and the European Space Agency. Back in 1970, early gamma-ray detectors revealed that the region from which these rays were being emitted stretched across about 10,000 light-years and shone with the brightness of roughly 10,000 suns. Decades later, in the year 2010, the Fermi Gamma-Ray Space Telescope made another astonishing discovery: two gigantic bubble-shaped regions of high-energy radiation located above and below the Milky Way's core. Each of these Fermi bubbles, as they became known, spans about 25,000 light-years in diameter, nearly 1/4 of the Milky Way's entire width. They rise far enough into the sky to reach the constellations of Grus and Virgo when viewed from the southern hemisphere. Later, radio observations using the Parkes telescope revealed that these bubbles also emit polarized radio waves, meaning that the radiation is aligned in a specific direction. This finding hinted that the bubbles are magnetized and likely created by powerful outflows of energy driven by intense star formation within the central 200 parsecs, or roughly 640 light-years, of our galaxy. On January 5, 2015, NASA reported another extraordinary event: an X-ray flare coming from Sagittarius A, the supermassive black hole at the Milky Way's center, suddenly became about 400 times brighter than usual. It was the most intense flare ever recorded from that region. Astronomers suggested that this powerful outburst might have been caused either by an asteroid being torn apart as it fell into the black hole, or by tangled magnetic field lines snapping and releasing energy in the surrounding gas. Beyond the central bar-shaped region of the galaxy, the Milky Way's disk is filled with stars and interstellar gas, organized into several great spiral arms. These spiral arms contain denser clouds of gas and dust than the surrounding regions and serve as cradles for new stars. Areas known as H2 regions, where hot young stars ionize nearby hydrogen gas, along with massive molecular clouds, help astronomers trace the pattern of star formation within these arms. However, the exact structure of the Milky Way's spiral pattern remains uncertain. Astronomers still do not fully agree on the precise number, shape, or arrangement of its arms. The galaxy's arms are far from perfect spirals. They branch, twist, and merge unpredictably. Near our Sun, the spiral structure appears especially irregular, and many researchers believe that the Sun resides in a smaller spur or minor arm rather than one of the major spiral arms. Estimates of the pitch angle, or how tightly the spiral arms wind around the galactic center, range from about 7 to 25 degrees. It is generally believed that 4 main spiral arms begin near the center of the Milky Way. Among these, 2 arms, the Scutum Centaurus arm and the Carina Sagittarius arm, lie within the Sun's orbit around the galactic center. Infrared surveys, which can see through the dust that hides many stars from view, have shown that the Scutum Centaurus arm contains roughly 30% more red giant stars than expected, confirming it as a major stellar arm. However, the Carina Sagittarius arm does not show a similar abundance of old stars, suggesting it may be primarily composed of gas and younger stellar material. From these observations, scientists have concluded that the Milky Way may have only 2 major stellar arms, the Perseus arm and the Scutum Centaurus arm, while the other two are rich in gas and newly formed stars but lack older populations. In December 2013, astronomers found evidence that the pattern of young stars and star-forming regions indeed fits the four-arm model, while older stars follow a two-arm structure. The reason for this difference is still not fully understood. The discovery of spiral arms in our galaxy dates back to the 1950s, when astronomer Hendrik van Woerden and his colleagues, using radio waves at 21 centimeters, detected what became known as the near 3 kiloparsec arm. This arm, found about 3 kiloparsecs, or roughly 10,000 light-years, from the galactic center, appeared to be expanding outward from the core at more than 50 kilometers per second. Decades later, in 2008, astronomer Tom Dame identified another similar feature, called the far 3 kiloparsec arm, located on the opposite side of the galaxy. Computer simulations published in 2011 suggested that the Milky Way's spiral structure might have formed through repeated gravitational encounters with a smaller neighbouring galaxy, the Sagittarius Dwarf Elliptical Galaxy. Other studies propose that the Milky Way might actually have two different spiral patterns, a fast-rotating inner pattern formed by the Sagittarius arm, and a slower, more tightly wound outer pattern formed by the Carina and Perseus arms. These two patterns might be connected by the Cygnus arm, creating a complex interlocking spiral design across the galactic disk. Far beyond the main spiral arms lies the Monoceros ring, a vast loop of gas and stars thought to have been stripped from other galaxies billions of years ago. However, some scientists argue that this structure might not be a separate ring at all, but rather an overdense region formed by the natural warp and flare of the Milky Way's outer disk. Indeed, the Milky Way's disk itself is not flat but gently twisted, forming a graceful S-shaped curve as it extends into space. Surrounding the Milky Way's flat, star-filled disk is a vast, roughly spherical halo made up of very old stars and hundreds of globular clusters, dense, ancient groups of stars bound together by gravity. Nearly 9 out of every 10 of these clusters lie within about 100,000 light-years from the galactic center, but a few outliers such as PAL 4 and AM1 have been found even farther away, at more than 200,000 light-years from the center. Interestingly, around 2 out of every 5 of these clusters move in a direction opposite to the Milky Way's general rotation, a motion known as a retrograde orbit. Unlike the smooth, elliptical orbits that planets follow around stars, many globular clusters travel along looping, flower-like paths known as rosette orbits, gracefully winding around the galaxy's heart over millions of years. While the galactic disk is full of thick clouds of dust that can block our view of certain wavelengths of light, the halo around it is much clearer, allowing light from distant stars to pass through more easily. Most new stars are born within the disk, especially in its bright spiral arms, the crowded lanes of gas, dust, and young hot stars that give the Milky Way its graceful swirling shape. The halo, by contrast, is a quiet realm. It lacks the cool gas needed to form new stars, so it contains only ancient ones that have been shining for billions of years. The disk also hosts open clusters, loose groups of relatively young stars, which are rarely found outside it. At the beginning of the 21st century, astronomers made a series of discoveries that expanded our understanding of the Milky Way's true structure. When scientists realized that the disk of the neighboring Andromeda galaxy stretches much farther than once believed, it raised the possibility that the Milky Way's disk might also extend farther into space. This idea was strengthened by the discovery of extensions to 2 of our spiral arms, the outer arm of the Cygnus arm, and a similar stretch in the Scutum Centaurus arm. Another remarkable discovery came with the Sagittarius Dwarf Elliptical Galaxy, a small companion galaxy orbiting the Milky Way. As it circles our galaxy, gravitational forces tear it apart, scattering its stars in a long looping ribbon of galactic debris. In the year 2004, astronomers detected a massive ring of stellar material orbiting the Milky Way within its plane. At first, this ring was thought to be the remains of a small galaxy called the Canis Major Dwarf, but later studies suggested it might instead be part of the Milky Way's own warped structure, a view supported by newer evidence gathered as recently as the year 2021. The Sloan Digital Sky Survey, which has mapped the northern skies in incredible detail, revealed an enormous, faint and diffuse structure within our galaxy. It spans an area about 5,000 times larger than the full moon in the sky, and does not fit neatly into existing models of the Milky Way. This mysterious collection of stars rises nearly straight up from the galactic plane, and many astronomers believe it may be the remains of a smaller galaxy currently merging with ours. This possible merging system, found in the direction of the constellation Virgo, about 30,000 light-years away, has been given the name Virgo Stellar Stream. But the Milky Way's halo is not made up of just stars. Observations from powerful space telescopes, including the Chandra X-ray Observatory, XMM Newton, and Japan's Suzaku, have shown that it also contains an enormous cloud of extremely hot gas. This gaseous halo stretches for hundreds of thousands of light-years, reaching distances nearly as far as the Large and Small Magellanic Clouds, two of our closest galactic neighbours. The temperature of this halo ranges from about 1 to 2.5 million kelvins, or roughly 1.8 to 4.5 million degrees Fahrenheit. Astonishingly, the total mass of this hot gas may be nearly as great as the mass of the Milky Way itself. Astronomers studying distant galaxies have discovered that, in the early universe, there was about 6 times more dark matter than ordinary, or baryonic matter. However, when scientists count up all the visible baryons in the modern universe, in stars, gas and dust, only about half seem to be accounted for. If the mass of this hot halo gas around the Milky Way truly equals that of the visible galaxy, it could explain the mystery of these missing baryons, suggesting they may have been hiding in plain sight within the halo all along. Within the Milky Way, stars and gas clouds orbit the galactic centre in complex differential motion, meaning that the time it takes to complete one orbit depends on their distance from the centre. For most of the galaxy, the orbital speed of stars remains surprisingly steady, ranging between about 200 and 220 kilometers per second. This behaviour differs from that of planets in our solar system, where objects farther from the Sun move more slowly due to the Sun's gravity. In the Milky Way, this nearly constant orbital speed means that stars farther out still move at almost the same pace as those closer in, tracing a flat rotation curve. If the Milky Way contained only the visible mass we can observe, stars, gas and dust, this curve would not be flat. The outer stars would move much more slowly. The fact that they do not reveals that there must be much more mass hidden throughout the galaxy, mass that does not emit or reflect light. This unseen material is what astronomers call dark matter. The Milky Way's rotation pattern matches that of other spiral galaxies across the universe, offering some of the strongest evidence that dark matter truly exists. Still, a small number of scientists propose an alternative view, that perhaps our understanding of gravity itself needs to be adjusted to explain these puzzling motions. The story of our Milky Way began more than 13.5 billion years ago, shortly after the great cosmic event known as the Big Bang. In those early moments, tiny ripples or overdensities in the sea of matter that filled the young universe began to grow under the pull of gravity. Some of these denser regions later became the seeds of globular clusters, ancient, tightly packed groups of stars that still sparkle faintly in the halo surrounding our galaxy today. These old stars are among the very first that ever shone in what would eventually become the Milky Way. Surprisingly, scientists believe that nearly half of all the matter in our galaxy may not have originated here at all, but was drawn in from faraway galaxies over billions of years. As the Milky Way gathered mass, it began to spin faster. Because of a fundamental law of physics called the conservation of angular momentum, this spinning caused the once roughly spherical cloud of gas and dust to flatten into a wide rotating disk. Within this great spiral disk, new generations of stars were born, among them our own Sun and the countless other young stars that now make up the bright plane of the Milky Way. Over its long life, the Milky Way has continued to grow and evolve. In its youth, it absorbed many smaller galaxies through a series of cosmic collisions, merging with them and pulling in their gas and stars. Even today, this process continues. Our galaxy is slowly consuming some of its nearest companions, including the Large and Small Magellanic Clouds, two bright satellite galaxies visible from the southern hemisphere. Streams of gas, such as the Magellanic Stream and the Smith Cloud, show clear evidence of this ongoing accretion, as they are being drawn into the Milky Way's gravitational embrace. Computer simulations suggest that about 11 billion years ago the Milky Way experienced a major merger with a large galaxy nicknamed the Kraken. However, since around 10 billion years ago, it appears to have enjoyed a relatively peaceful life, avoiding further collisions with large galaxies, a rare occurrence for spiral galaxies of its size. Its neighbour, the Andromeda Galaxy, has had a much more turbulent history, shaped by several major mergers in more recent times. Modern observations have revealed that both the Milky Way and the Andromeda Galaxy occupy a curious place in what astronomers call the Green Valley. This is a region in the galaxy colour magnitude diagram that marks the slow transition between the blue cloud of youthful star-forming galaxies and the red sequence of older galaxies where star birth has largely ceased. Galaxies in the Green Valley are slowly running out of the cold gas needed to form new stars. If our galaxy continues along this path, star formation may fade away entirely in about 5 billion years, even though a brief burst of new star formation is expected when the Milky Way and Andromeda collide in the distant future. Right now, the Milky Way remains one of the brightest and reddest spiral galaxies still actively forming stars, though it is gradually aging and becoming redder over time. The oldest objects in the Milky Way are the globular clusters, which provide astronomers with clues about the galaxy's true age. To estimate the ages of individual stars, scientists measure the tiny amounts of radioactive elements like thorium and uranium they contain. By comparing the current abundance of these elements to how much was originally present, a method known as nucleocosmochronology, they can determine how long the star has existed. Another approach involves studying white dwarfs, stellar remnants that slowly cool over time. By measuring how cool the oldest white dwarfs have become, researchers can estimate their ages. This method has been used to determine that the globular cluster known as M Found is about 12.5 billion years old, setting a firm lower limit for the Milky Way's age. In November of the year 2018, astronomers announced the discovery of one of the oldest known stars in the entire universe. At roughly 13.5 billion years old, this tiny star was formed almost entirely from material created in the Big Bang itself, making it a direct witness to the universe's earliest era. Its discovery even hinted that the Milky Way might be several billion years older than previously believed. Other ancient stars in the Milky Way's halo have been dated to about 13 billion years old using highly precise spectroscopic observations that measure the faint signatures of radioactive elements. Another famous star, called the Methuselah star, has been estimated to be between 12 and nearly 14 billion years old, making it one of the oldest known stars in the galaxy. Studies using advanced adaptive optics, which correct for the blurring effects of Earth's atmosphere, have revealed that the stars in the central bulge of the Milky Way are around 12.5 billion years old. The stars in the galactic disk, however, are younger. Measurements suggest that the thin disk began forming roughly 9 billion years ago, nearly 5 billion years after the first halo stars appeared. During this period, star formation seems to have slowed down dramatically, as the interstellar gas became too hot to collapse into new stars at the same rate as before. Astronomers have discovered that the Milky Way's many satellite galaxies are not randomly scattered, but appear to form part of a vast ring-like structure that stretches nearly 500,000 light-years across and about 50,000 light-years wide. Such structures may have formed long ago when a large system broke apart or when powerful gravitational interactions between galaxies pulled great tails of gas into space, tails that later condensed into small dwarf galaxies. In about 4 billion years, a similar event is expected when our Milky Way collides with the Andromeda Galaxy, a cosmic encounter that will reshape both galaxies, creating new stars, new worlds, and perhaps a beautiful new spiral galaxy to inherit the heavens. The Milky Way and the Andromeda Galaxy form a pair of massive spiral galaxies that move together as part of a larger family of about 50 galaxies known as the Local Group. This group is surrounded by a vast empty region called the Local Void, which lies within a thin sheet of galaxies known as the Local Sheet. The Local Sheet in turn belongs to an even grander structure called the Virgo supercluster. Surrounding the Virgo supercluster are enormous cosmic voids that contain very few galaxies. The Microscopium Void lies to the north, the Sculptor Void to the left, the Boötes Void to the right, and the Cain's Major Void to the south. These enormous regions constantly change shape over time, forming long, thread-like chains of galaxies known as cosmic filaments. The Virgo supercluster itself is slowly being pulled toward an even greater concentration of matter, known as the Great Attractor, which is part of a gigantic supercluster complex called Laniakea, the immense continent of galaxies to which our Milky Way ultimately belongs. Two smaller irregular galaxies and many tiny dwarf galaxies orbit around the Milky Way. The largest of these companions is the Large Magellanic Cloud, which is about 32,200 light-years wide. It has a smaller partner, the Small Magellanic Cloud, and together they form a striking pair in the southern sky. From these two galaxies extends a long trail of hydrogen gas known as the Magellanic Stream, stretching across 100 degrees of the sky. Astronomers believe this stream was torn away from the Magellanic Clouds as the Milky Way's gravity pulled on them during their repeated close encounters. Several other dwarf galaxies circle the Milky Way as well. These include the Canis Major Dwarf, which is the closest, the Sagittarius Dwarf Elliptical Galaxy, the Ursa Minor Dwarf, the Sculptor Dwarf, the Sextans Dwarf, the Fornax Dwarf, and the Leophas Dwarf. Some of the tiniest among them, such as the Carina Dwarf, the Draco Dwarf, and the Leotas Dwarf, are only about 500 light-years across, incredibly small compared to the Milky Way's immense size. Astronomers suspect that more faint dwarf galaxies still remain undiscovered. In the year 2015, 9 new small satellite galaxies were found in just a small area of the sky, suggesting that many others might be hidden in the darkness. Some ancient dwarf galaxies have already been completely absorbed by the Milky Way, including the one that originally formed the great star cluster known as Omega Centauri. In the year 2005, and again confirmed in 2012, researchers found something unexpected. Most of the Milky Way's small satellite galaxies are arranged in a single huge flat disk and move in the same general direction. This discovery was surprising because according to standard theories of galaxy formation, these satellites should have formed in separate dark matter halos and should be scattered randomly through space, moving in many different directions. The reason for this unusual alignment is still a mystery that scientists are trying to explain. In January of 2006, another discovery shed light on a long-standing puzzle. The Milky Way's disk is slightly warped or bent, and new observations showed that this warp is actually a wave or ripple created by the gravitational pull of the large and small Magellanic Clouds as they orbit our galaxy. Although these two small galaxies together make up only about 2% of the Milky Way's total mass, computer models reveal that their motion through space creates a wake in the surrounding dark matter, amplifying their influence and making them powerful enough to bend the Milky Way's disk. Current measurements show that the Andromeda Galaxy is moving toward the Milky Way at a speed between 100 and 140 kilometers per second, or roughly 220,000 to 310,000 miles per hour. In about 4 1/3 billion years, the two galaxies are expected to collide. Even though this sounds dramatic, the actual chance of stars crashing into one another is extremely small because of the enormous distances between them. Instead, their vast clouds of stars, gas, and dark matter will slowly merge over several billion years to form a single giant galaxy, either an enormous elliptical galaxy or perhaps a massive new spiral. The entire process could take around 6 billion years to complete. Even though the laws of special relativity say there is no single, preferred, place in space to measure motion, astronomers can still describe how the Milky Way moves compared to large-scale cosmic reference points. One of these is called the Hubble flow, the general outward movement of galaxies caused by the expansion of the universe. Individual galaxies like ours move with their own small, peculiar velocities relative to this overall expansion. When comparing to the Hubble flow, scientists must consider a large enough region of space that local motions average out. Based on these measurements, the Milky Way is travelling at roughly 630 kilometers per second, about 1,400,000 miles per hour, relative to the local cosmic background. Our entire local group, which includes the Milky Way, Andromeda, and many smaller galaxies, is part of the larger Virgo supercluster. It is centered near the Virgo cluster, and even though the local group and the Virgo cluster are moving apart at about 967 kilometers per second, a little over 2,160,000 miles per hour, this is actually slower than expected because their mutual gravity partially counteracts the expansion of space. Another useful cosmic reference is the frame of the cosmic microwave background, CMB, the faint afterglow of the Big Bang that fills the universe. In this frame, the Milky Way is moving at about 552 kilometers per second, around 1,235,000 miles per hour, toward a point in the sky near the constellation Hydra. This motion has been carefully measured by satellites such as the Cosmic Background Explorer, COBE, and the Wilkinson Microwave Anisotropy Probe, DUC-MAP. These spacecraft detect a small dipole pattern in the CMB. The radiation appears slightly hotter, blue-shifted, in the direction of our motion, and slightly cooler, red-shifted, in the opposite direction, revealing how our entire galaxy glides through the cosmic sea. From the surface of Earth, without using any telescope, the human eye can see roughly 6,000 stars sprinkled across the night sky. At first, that might sound like a staggering number, but in truth, it represents only a tiny portion of what truly exists in space. For every single star visible to the naked eye, there are more than 20 million others that remain unseen. Most of these hidden stars are simply too faint, too distant, or buried behind immense clouds of cosmic dust that block their light from reaching us. Every one of these visible and invisible stars belongs to our own galaxy, the Milky Way. Yet the Milky Way is only one among countless others scattered across the universe. For instance, the neighbouring Andromeda galaxy is even larger than ours. Each galaxy is a vast cosmic system made up of billions of stars, along with their planets, moons, comets, and asteroids. They also contain remnants of dead stars such as white dwarfs, neutron stars and black holes, as well as enormous clouds of interstellar gas and dust. Astronomers now estimate that the entire universe may contain about 100 billion galaxies, though the true number might be far greater since our instruments cannot yet detect them all. Between these galaxies stretches intergalactic space, a boundless realm filled with only a faint trace of gas, so thin that it would be almost a perfect vacuum. When one thinks about the size of our solar system, a region so large that even light takes hours to cross it, and then realizes that it is just one among countless others within a single galaxy, it becomes easier to understand why scientists often describe the universe as practically infinite. This perspective reveals just how small Earth and all of humanity truly are within the grand structure of the cosmos. Over the past century, astronomers have made remarkable discoveries about the material that exists between the stars, known as the interstellar medium. Using powerful radio and X-ray telescopes, they found that this vast space is filled mostly with thin clouds of ionized hydrogen gas, along with dust particles and streams of energetic cosmic rays. Within dense regions of this gas and dust, gravity can cause the material to collapse, leading to the birth of new stars. Thus, the interstellar medium acts as both a graveyard of old stars and a cradle for new ones. Even within our own solar neighbourhood, mysteries remain. Just beyond the planets lies a wide region known as the Kuiper Belt, a giant ring of icy worlds, comets, and debris located between about 30 and 50 astronomical units from the Sun. An astronomical unit is the average distance from Earth to the Sun, around 93 million miles. Encircling the entire solar system is the heliosphere, a vast bubble formed by the solar wind, a continuous flow of charged particles released by the Sun. This bubble acts as a protective shield, preventing most high-energy cosmic rays from entering the inner solar system. Without this invisible barrier, Earth might have been bombarded by harmful radiation, making the development of life very different, or perhaps impossible altogether. At the edge of this enormous bubble lies the interstellar boundary, where the solar wind meets the pressure of the interstellar medium. Inside this boundary, the solar wind carries plasma, an electrically charged gas, outward from the Sun. Eventually, however, it slows down when it encounters the opposing forces of space beyond. This first slowdown occurs at a region called the termination shock, where the solar wind, which once travelled at speeds between about 370 and 430 miles per hour, suddenly drops to only about 62 miles per hour. Beyond this point lies the heliosheath, a region where the solar wind continues to slow and mix with interstellar material. At the very edge lies the heliopause, the final border of the Sun's magnetic influence. This distant frontier, located around 11 billion miles, or roughly 18 billion kilometers from the Sun, marks the beginning of true interstellar space. Since the dawn of space exploration, only 2 human-made spacecraft have ever crossed this distant boundary. The first was Voyager 1, launched in the year 1977. It took more than 30 years for this brave little probe to reach the heliopause and venture into interstellar space. Once it crossed that border, Voyager 1 continued sending valuable data back to Earth, providing humanity with its first direct look into a region no longer controlled by the Sun. Its achievement remains one of the most extraordinary milestones in the history of science. The story of exploration does not end there. After Pluto was discovered in the year 1930 by Clyde Tombaugh, astronomers began to wonder whether this small, icy world was alone in the far reaches beyond Neptune. Over the following decades, many scientists proposed that there might be a region filled with numerous frozen bodies orbiting far from the Sun. This idea would later become the basis for what we now call the Kuiper Belt. However, it was not until the year 1992, more than 60 years after Pluto's discovery, that the existence of this distant region was finally confirmed by direct observation. Because many astronomers had suggested similar ideas independently, there remains some debate about who truly deserves credit for first proposing it. One of the earliest scientists to suggest that more objects might exist beyond Neptune was Frederick C. Leonard. Shortly after Pluto's discovery in 1930, Leonard asked whether Pluto could be the first of a series of ultra-Neptunian bodies, hinting that many others still awaited discovery. In that same year, another astronomer, Armin O. Leuschner, also proposed that Pluto might be one of many long-period planetary objects yet to be found. More than a decade later, in the year 1943, Kenneth Edgeworth published a paper in the Journal of the British Astronomical Association. He argued that in the distant region beyond Neptune, the leftover material from the formation of the solar system was too thinly spread to combine into full-size planets. Instead, he suggested that this material gathered into countless smaller icy bodies. He reasoned that the outer solar system must therefore be filled with a vast population of small worlds, and that occasionally one of them might drift inward toward the Sun, appearing to us as a comet. In the year 1951, Gerard Kuiper published a paper in Astrophysics, a topical symposium, where he talked about the idea of a disk-like structure that had formed in the early days of the solar system. He thought this disk was made up of leftover icy pieces which had broken apart over time, much like star clusters that eventually come apart. In another paper, based on a talk he gave in 1950, titled On the Origin of the Solar System, Kuiper described an outermost part of the solar nebula, stretching from 38 to 50 astronomical units away from the Sun. In this area, he believed, ices of water, ammonia and methane came together into objects as big as 1 kilometre or more. According to him, these clumps could explain comets in terms of size, makeup and number. Kuiper also said that Pluto, then thought to be as large as Earth, was moving through this whole region, scattering many of these bodies across the solar system. If his guess about Pluto's size had been right, then the Kuiper Belt as we know it would not exist today. Other scientists continued to build on the idea in the following decades. In 1962, physicist Alistair G.W. Cameron suggested that the edge of the solar system might hold a huge amount of small material. In 1964, Fred Whipple, the astronomer known for his dirty snowball idea of comets, proposed that a comet belt could even be large enough to explain the strange movement of Uranus, which had led astronomers to search for a so-called Planet X. His idea was later proven wrong by observations, but it kept the discussion going. In 1977, Charles Cowell found the icy body later named 2060 Chiron, which orbits between Saturn and Uranus. He used the same type of device, a blink comparator, that Clyde Tombaugh had once used to find Pluto nearly 50 years earlier. In 1992, another similar object, later called 5145 Pholus, was found. Today, we know of a whole group of such comet-like bodies, called the Centaurs, which orbit between Jupiter and Neptune. These orbits are unstable, lasting only a few million years, so scientists decided that they must be replaced from a larger source farther out in the solar system. More proof for the Kuiper Belt came from studying comets. Astronomers had long known that comets could not last forever. Each time a comet goes near the Sun, the heat makes its icy surface turn into gas, slowly wearing it down. Since comets still appear often in our skies, there must be some place in space that keeps making new ones. One possible source is the Oort cloud, a huge spherical swarm of icy objects suggested in the year 1950 by Dutch astronomer Jan Oort. The Oort cloud may reach out to 50,000 astronomical units from the Sun, and is believed to be where long-period comets come from, those with orbits lasting thousands of years, such as the famous Hale-Bopp comet. There is another group of comets known as short-period comets or repeating comets. These are the comets that return fairly quickly, making a full trip around the Sun in less than 200 years. A well-known example is Halley's Comet, which comes back into the night sky about every 76 years. By the 1970s, astronomers noticed something strange. The number of short-period comets being found did not fit the idea that they were all coming only from the faraway Oort cloud. For a comet to travel from the Oort cloud into the inner solar system and then become a short-period comet, it would first have to be caught by the gravity of the giant planets. This process seemed far too slow and unlikely to explain the large number of short-period comets actually seen. In the year 1980, Uruguayan astronomer Julio Fernandez published a paper in the monthly notices of the Royal Astronomical Society. In his calculations, he showed that for every short-period comet that managed to reach the inner solar system from the Oort cloud, about 600 others would be lost forever, thrown out into interstellar space. To solve this puzzle, Fernandez suggested that there must be another source much closer to the Sun, a belt of comets lying between 35 and 50 astronomical units from the Sun. A few years later, in 1988, 3 Canadian astronomers, Martin Duncan, Tom Quinn and Scott Tremaine, tested this idea by running computer models. They wanted to see if all the comets we see could really have come only from the Oort cloud. Their results backed up Fernandez's belief. The Oort cloud alone could not explain the patterns seen. Short-period comets tended to stay near the plane of the solar system, while Oort cloud comets could come from almost any direction in the sky. When they added a belt, as Fernandez had described, the models finally matched reality. Reportedly, because the words Kuiper and comet belt appeared in the first line of Fernandez's paper, Tremaine decided to name this supposed region the Kuiper belt. Meanwhile, in 1987, astronomer David Jewett, who was then working at the Massachusetts Institute of Technology, MIT, became more and more curious about what he called the clear emptiness of the outer solar system. He believed there had to be more beyond Pluto. Jewett encouraged his graduate student Jane Liu to help him search for objects past Pluto's orbit, telling her, "If we don't do it, nobody will." Using telescopes at the Kitt Peak National Observatory in Arizona and at the Cerro Tololo Inter-American Observatory in Chile, they began their search. Their method was very similar to the one Clyde Tombaugh used to find Pluto in the year 1930, comparing photographic plates with a tool called a blink comparator. At first, checking each pair of plates took around 8 hours, but their work became much faster with the arrival of electronic charge-coupled devices, or CCDs. Although early CCDs could only capture a small part of the sky at once, they were far more sensitive than photographic plates. A CCD could keep about 90% of the light that reached it, while traditional photographs kept only about 10%. Another benefit was that the blinking process could now be done directly on a computer screen instead of by hand. Today, almost all astronomical observations use CCDs. In 1988, Jewett moved to the Institute of Astronomy at the University of Hawaii. Liu later joined him, and together they used the University of Hawaii's 2.24-meter telescope on Mauna Kea. As CCD technology got better, detectors grew to cover areas of 1024 by 1024 pixels, making searches much faster. After 5 long years of careful searching, on the 30th of August 1992, Jewett and Liu finally announced their discovery, the first confirmed object in the Kuiper belt, which was given the temporary name 1992 QB1. This object was later officially named Albion and catalogued as number 15,760. Just 6 months later, they found a second object, later catalogued as 181,708 1993 FW. From then on, discoveries came quickly. By the year 2018, astronomers had found more than 2,000 Kuiper belt objects. In the first 2 decades alone, from 1992 to 2012, over 1,000 bodies were found in the area, showing that the solar system's outer belt is full of icy objects beyond Pluto and Albion. Even in the 2010s, though, scientists still did not completely understand the size and nature of Kuiper belt objects. The first close-up studies had to wait for spacecraft. In the year 2015, NASA's New Horizons mission flew past Pluto and its moons, giving people the first detailed look at the Plutonian system. Then, in the year 2019, the same spacecraft visited another Kuiper belt object, Arrokoth, giving the first direct pictures of one of these faraway bodies. Later studies showed an even more complicated story. Astronomers now know that the Kuiper belt itself is not where short-period comets are born. Instead, these comets mostly come from a related area called the scattered disk. The scattered disk was made long ago when Neptune moved outward from the Sun. In doing so, it reshaped the early Kuiper belt. Part of the group was left behind in stable orbits, forming the Kuiper belt as we see it, while another part was left in unstable places where Neptune's gravity could still move them around. These unstable objects became the scattered disk, and it is now thought to be the real source of most repeating comets. Different names are sometimes used for this area. Some call it the Edgeworth Kuiper Belt to include the Irish astronomer Kenneth Edgeworth, though others argue that neither Edgeworth nor Gerard Kuiper described anything like what we see today. Astronomer Fred Whipple, in fact, came closer to the modern idea. David Jewett himself has said that Fernandez deserves the most credit for predicting the Kuiper Belt. Kuiper Belt objects, or KBOs, are sometimes called Kuiperoids, a name suggested by Pluto's discoverer Clyde Tombaugh. In modern astronomy, however, the more neutral term Trans-Neptunian Object, TNO, is preferred, since it refers broadly to any object moving around the Sun beyond Neptune, not just those in the Kuiper Belt. At its greatest reach, if we include its farthest parts but leave out the scattered disk, the Kuiper Belt stretches across a distance from about 30 astronomical units to about 55 astronomical units away from the Sun. The main part of the belt is usually described as lying between two special points, known as orbital resonances with Neptune. The inner edge is the so-called 2 to 3 resonance at roughly 39.5 astronomical units, while the outer edge is the 1 to 2 resonance at around 48 astronomical units. The Kuiper Belt is not a thin, flat ring. Instead, it is surprisingly thick. Most of its objects can be found spread up to 10 degrees above and below the ecliptic, the flat plane in which the planets move, and some even farther, scattered in a wider cloud. Because of this, the belt is shaped more like a donut or torus rather than a narrow band. On average, the belt itself is tilted by about 1.86 degrees from the ecliptic. Neptune plays an important part in shaping the Kuiper Belt. Its strong pull, over the course of billions of years, the age of the solar system can make the orbits of objects in certain areas unstable. These objects may then be pushed inward toward the planets, outward into the scattered disk, or even completely out of the solar system into the space between the stars. This effect creates clear gaps in the spread of Kuiper Belt objects, much like the Kirkwood gap seen in the asteroid belt. For example, in the area between 40 and 42 astronomical units, no object can stay stable for long, and so anything found there today must have arrived only recently. Between the 2 to 3 and the 1 to 2 resonances with Neptune, roughly 42 to 48 astronomical units, objects can stay in their paths for very long times without being disturbed. This area is called the classical Kuiper Belt, and it holds about 2/3 of all the Kuiper Belt objects discovered so far. The very first modern KBO ever found in the year 1992, first called 1992 QB1 but later named Albion, belongs to this group. Because of this, classical objects are often called cubewanos, a nickname based on the letters and numbers of Albion's first name. The International Astronomical Union has rules saying that classical KBOs must be named after mythological beings linked to creation. The classical Kuiper Belt is actually made up of two different groups. The first, called the dynamically cold group, travels in paths that look very much like the planet's orbits, almost round, with eccentricities less than 0.1 and staying close to the flat plane of the solar system, tilted by no more than 10 degrees. Within this cold group is a denser collection of objects, called the kernel, found at distances between 44 and 44.5 astronomical units. The second group, called the dynamically hot group, has orbits tilted much more sharply, sometimes by as much as 30 degrees. The words hot and cold here do not refer to heat, but are borrowed from the way particles behave in a gas. The hotter they are, the faster and more uneven their motions become. The two groups differ in more ways than just their orbits. The cold objects tend to look redder and brighter, have more binary systems, and lack very large bodies. They also have a different size pattern compared with the hot group. Interestingly, the total mass of the cold group is about 30 times smaller than that of the hot group. Scientists think that these differences in colour and brightness show differences in makeup, suggesting that the two groups formed in different places. The hot group is thought to have formed closer to Neptune's first orbit and was thrown outward during the movement of the giant planets. The cold group, on the other hand, seems to have formed in its current place, since fragile binary systems would not likely survive repeated meetings with Neptune. Some scientists think that the colour differences may also come from changes on their surfaces over long periods of time. Another important feature of the Kuiper Belt involves orbital resonances with Neptune. If an object's path matches a simple ratio with Neptune's path, it can be locked in a steady rhythm, allowing it to remain stable. For example, in the 2 to 3 resonance, an object circles the Sun twice for every 3 paths of Neptune. Pluto is the most famous member of this group, along with about 200 other known objects. These are called plutinos. Although Plutino's paths cross Neptune's, their resonance makes sure they never actually hit each other. Plutinos usually have very stretched paths, showing that they were likely placed there by Neptune's movement. According to International Astronomical Union rules, all Plutinos must be named after gods of the underworld, following Pluto's example. Farther out, the 1-2 resonance is found at about 47.7 astronomical units. It is much less crowded, and its members are sometimes called tutinos. Other resonances also exist, such as 3-4, 3-5, 4-7, and 2-5. Neptune also has Trojan objects that share its path, sitting at stable points ahead of and behind the planet. These Trojans are locked in a 1-to-1 resonance with Neptune and often have long-lasting stable paths. Interestingly, there is a clear lack of objects with main axes inside 39 astronomical units that cannot easily be explained by today's resonances. The main idea is that when Neptune moved outward in the distant past, its shifting pull swept through this area, pushing out or capturing most of the bodies that once lived there. Astronomers studying the Kuiper belt have noticed something strange at its far edge. At a distance of about 48 astronomical units from the Sun lies what is called the 1-2 resonance with Neptune. Beyond this point, very few objects have been found, making it look like the outer edge of the classical Kuiper belt. However, scientists are still not sure if this really is the final edge, or if it simply marks the start of a wide, nearly empty gap. A few objects have been found much farther out, near the 2-5 resonance at about 55 astronomical units, well beyond the main classical belt. Earlier predictions said that large numbers of bodies should exist between these two resonances, but so far observations have not confirmed this. Early models of the Kuiper belt, based on the estimated mass needed to form planets such as Uranus and Neptune, and even bodies as large as Pluto, suggested that the number of large objects should actually increase beyond 50 astronomical units, possibly by as much as a factor of 2. Instead, astronomers found the opposite, a sudden and sharp drop in the number of objects. This sudden decrease is called the Kuiper cliff, and its cause is still unknown. In the year 2003, astronomers David Bernstein, David Trilling, and their team confirmed that this drop is real, and not just the result of missing objects because of limited telescope searches. Several ideas have been suggested. Perhaps the material at far from the Sun was too thin, or too spread out to come together into large bodies. Or maybe later events destroyed or scattered those objects. Patrick Likauka of Kobe University even suggested that the pull of an undiscovered planet, perhaps similar in size to Earth or Mars, could be the reason. Recent studies of data from trans-Neptunian objects, up to September of the year 2023, show that the pattern of objects at the far edge of the classical belt looks like the outer main asteroid belt in the inner solar system. Both seem to contain mysterious gaps. In the Kuiper belt, a gap appears around 72 astronomical units from the Sun, far away from any known resonances with Neptune. In the asteroid belt, a similar gap is caused by Jupiter's 5-6 resonance at about 5.875 astronomical units. Even after many years of study, the exact beginning and shape of the Kuiper belt remain uncertain. To solve these mysteries, astronomers use wide-field survey telescopes. One of the first, Pan-STARRS-1, finished its main science mission in the year 2014, and its full dataset was released in the year 2019, greatly increasing the number of known Kuiper belt objects. Future surveys, especially with the Large Synoptic Survey Telescope, are expected to discover thousands more objects and provide important clues. The Kuiper belt is believed to be made up of planetesimals, the leftover pieces from the original disk of dust and gas that surrounded the young Sun. These pieces never grew large enough to become full planets. The biggest of them, such as Pluto, are less than 3,000 kilometers across. Studies of the craters on Pluto and its moon Charon suggest that smaller Kuiper belt bodies did not form by slowly joining together from tiny kilometer-sized pieces. Instead, they likely formed directly as much larger objects, tens of kilometers wide. Ideas for how this happened include the collapse of clouds of small pebbles inside swirling areas of gas in the early solar system, or through processes known as streaming instabilities. In some cases, these collapsing clouds may have split into two, creating binary objects that move around each other. Modern computer models show that the Kuiper belt was strongly shaped by the giant planets, especially Jupiter and Neptune. In fact, Uranus and Neptune could not have formed where they are now because there was not enough material in that region. They probably formed closer to Jupiter and then moved outward. As the early solar system changed, the paths of Saturn, Uranus and Neptune shifted outward, while Jupiter moved slightly inward. Eventually, Jupiter and Saturn reached a precise 1:2 resonance, meaning Jupiter went around the Sun twice for every one path of Saturn. This powerful pull between them made the orbits of Uranus and Neptune unstable, sending them outward onto stretched paths that disturbed the ancient disk of planetesimals. When Neptune's path was still stretched out, its gravitational pull overlapped in several areas, and small building blocks of planets moved in a wild, disorderly way, spreading outward as far as Neptune's 1:2 resonance. Over time, as Neptune's path became more rounded, it slowly moved outward to where it is now. During this movement, many of those small bodies got caught in gravitational patterns, while others escaped into steady paths. Some were thrown inward and became Jupiter's Trojans, the odd moons of giant planets, or parts of the outer asteroid belt. Most, however, were tossed outward and completely thrown out of the solar system. This process may have cut down the Kuiper belt's original number of objects by more than 99%. To explain these events, scientists made a theory called the Nice model, named after the city of Nice in France, where it was first developed. This model does a good job of explaining many things about the Kuiper belt, such as its cold and hot groups, its objects in resonances, and the scattered area. However, it still has some problems. For example, it predicts slightly more stretched orbits for the regular Kuiper belt objects than what astronomers actually see. It also cannot completely explain why so many pairs of objects still exist in the cold belt when Neptune's pull should have broken them apart. Later versions of the Nice model suggest that the solar system originally had not 4 but 5 giant planets, including one extra icy giant. About 400 million years after the solar system formed, this extra planet was pushed onto a path that crossed Jupiter's orbit and was eventually thrown out into deep space. The remaining planets then kept moving until most of the small icy and rocky material was cleared away. In these newer models, Neptune's outward journey helps explain how the hot and cold groups of the Kuiper belt formed. When Neptune moved from 24 to 30 astronomical units over about 30 million years, its movement caught some objects in resonances and scattered others into different paths. The cold part of the Kuiper belt may have kept its local objects because Neptune's orbit stayed fairly round, avoiding the chaotic scattering predicted by the first model. Even today, the Kuiper belt acts like a natural lab for learning about the earliest history of the solar system. Every new discovery of a faraway icy world helps scientists understand how the giant planets moved, how small bodies formed, and how our planetary system became what it is today. Because the Kuiper belt is very far from the Sun and the big planets, the objects there are believed to be much less changed by the violent events that shaped most of the other worlds in the solar system. For this reason, learning what these Kuiper belt objects, or KBOs, are made of can give us important clues about the original materials of the solar system when it first formed billions of years ago. However, studying them is very hard. These objects are not only very small compared to planets, but they are also extremely far from Earth. This makes it very difficult to find out what they are made of. Astronomers usually use a method called spectroscopy to figure out what faraway space objects are made of. In this method, the light coming from an object is split into its different colours, creating something like a rainbow. This rainbow-like picture is called a spectrum. Different materials absorb light at different colours, and when astronomers look at the spectrum of an object, they see dark lines, called absorption lines, where certain substances have absorbed specific colours of light. Since every element and compound has its own special pattern of lines, astronomers can tell what the object is made of by studying this light pattern. Studies have shown that Kuiper belt objects are mostly made of a mix of rock and various types of ice. These include water ice, methane ice, and ammonia ice. Because the temperature in the Kuiper belt is only about 50 degrees above absolute zero, around minus 223 degrees Celsius, many substances that would normally be gases near the Sun stay frozen solid in this faraway region. Still, scientists know the exact mix of rock and ice for only a few KBOs, usually the larger ones whose size and weight have been measured. Astronomers measure size in several ways: by taking clear pictures with strong telescopes like the Hubble Space Telescope, by watching how long an object blocks the light of a distant star, an event called an occultation, or more often, by estimating how much sunlight it reflects, its brightness, or albedo, and comparing that to its heat radiation in the infrared. Weight can only be found for objects that have moons, because the moon's movement gives the needed gravity data. So, densities are known for only a few pairs of objects. The densities range from less than 0.4 grams per cubic centimetre to about 2.6 grams per cubic centimetre. The least dense objects are thought to be mostly icy, with lots of empty space inside them, making them spongy. The densest ones are believed to be mostly rocky with just a thin layer of ice. In general, smaller Kuiper belt objects have lower densities, while larger ones are heavier and more solid. One possible reason is that collisions between objects may have removed some of the ice, leaving behind harder, rockier bodies. When astronomers first studied KBOs, they couldn't yet see much detail, so they focused on something simple: their colours. Early studies showed that KBOs range from grey to deep red. This wide variety suggested that their surfaces are made of very different materials, from dirty ice mixtures to carbon-rich substances. This was surprising because scientists had expected all KBOs to look the same, dark and dull, after losing most of their icy parts over time due to cosmic rays. Different ideas were suggested to explain the colour range, such as impacts or the release of gases from inside. In the year 2001, astronomers David Jewett and Jane Liu studied the spectra of many Kuiper belt objects and found that the wide colour range couldn't be explained just by random impacts. They suggested instead that sunlight and radiation might chemically change methane on their surfaces, creating complex organic substances called tholins, which give a reddish colour. The dwarf planet Makemake, for example, has been shown to have several hydrocarbons formed by radiation acting on methane, such as ethane, ethylene, and acetylene. Although most KBOs are still too faint to show clear spectral details, astronomers have had some success. In the year 1996, Robert H. Brown and his team studied the KBO known as 1993 SC and found that its surface makeup is very similar to that of Pluto and Neptune's moon Triton, with large amounts of methane ice. Smaller KBOs, however, are often known only by their colour and brightness. Many fall into two types: grey ones with low reflectivity, low albedo, and very red ones with higher reflectivity. A possible reason for this difference is the presence or lack of hydrogen sulfide on their surfaces. Objects far enough from the sun kept their hydrogen sulfide, which, when hit by radiation, turned them reddish. The largest Kuiper belt objects like Pluto and Quaoar are different again. Their surfaces are rich in easily evaporating materials like methane, nitrogen, and carbon monoxide. Because these substances can sometimes turn into gas and then freeze again as snow in the freezing 30 to 50 Kelvin range of the Kuiper belt, they stay on the surfaces of these bigger bodies. Their ability to hold onto these materials depends on both gravity and temperature. Water ice has been found on several objects, including members of the Haumea family like 1996 to 66, mid-sized ones like 38,628 Huya and 20,000 Varuna, and even some smaller ones. Also, ordered, crystalline water ice has been found on both large and medium KBOs, including 50,000 Quaoar, where ammonia hydrate has also been discovered. This mix of crystalline ice and ammonia suggests that some of these bodies may have had some interactivity in the past, with ammonia lowering the melting point of water and allowing limited surface movement to happen. Even though the Kuiper belt stretches across a huge area of space, the total mass of all the objects in it is surprisingly small. Scientists think that the so-called hot population, the group of objects moving in more tilted and stretched paths, adds up to only about 1% of Earth's mass. The cold population, which moves in more rounded and steady paths, is even smaller, at only about 0.03 of 1% of Earth's mass. Researchers believe that the hot group is what's left of a much larger collection of objects that first formed closer to the Sun but were pushed outward when the giant planets moved to their current positions. The cold group, on the other hand, is thought to have formed right where it is, without much movement since the early days of the solar system. The latest careful estimate, published in the year 2018, found that the whole Kuiper belt has a total mass of about 1/50th of Earth's mass. This estimate comes from measuring the tiny pull that the belt's gravity has on the planet's orbits. But this small total mass creates a problem. For the large Kuiper belt objects, those over about 100 kilometers, around 62 miles wide, to have formed, there must have been much more material in that area when the solar system was young. If the cold Kuiper belt had always been as light and thin as it is now, these large bodies couldn't have formed just by small ones bumping and sticking together. Also, The slanted and stretched paths of many objects mean that impacts would often be violent, breaking them apart instead of helping them grow. It also seems unlikely that the cold group once had a lot more material and then lost it later. Neptune's gravity today is far too weak to have cleared away such a large amount, and endless collisions can't explain it either, since fragile binary systems still exist in the cold belt. They wouldn't have survived if the collisions had been too destructive. Because of these problems, many scientists now think that the biggest Kuiper belt objects may have formed in another way, not from random impacts, but by the direct collapse of thick clouds of small icy pebbles. When it comes to the size of Kuiper belt objects, they follow certain number patterns known as power laws. In simple terms, this means the number of objects depends on their size in a regular way. The smaller the object, the more of them there are. Early studies, based on how bright these objects look, suggested that for every one object between 200 and 400 kilometers wide, there are about 8 objects between 100 and 200 kilometers wide. More recent studies have shown that the hot and cold groups of the Kuiper belt follow different patterns. Among the hot objects, large bodies follow a sharp slope, meaning there are not many very large ones, while small ones are more common, with a turning point at about 110 kilometers. The cold objects show an even sharper slope for large bodies, with the change happening at about 140 kilometers. Other groups, such as the scattering objects, the Plutinos, which are in orbital lock with Neptune, and the Neptune Trojans, show patterns similar to the hot group. Some of these groups may even show a sudden drop in numbers below a certain size, a feature scientists call a dip. This could mean that smaller bodies were later made only as broken pieces from larger ones, or that the original group simply never made many tiny objects to start with. The very smallest Kuiper belt objects, those less than 1 kilometer across, are so faint that they cannot be seen directly, even with strong telescopes like the Hubble Space Telescope. Instead, they have been found through a method called stellar covering, when one of these tiny objects briefly passes in front of a faraway star, blocking its light for just a split second. In December of 2009, a team led by Hilke Schlichting reported finding such an object in saved Hubble data taken in March of 2007. The object had an estimated radius of about 520 meters, meaning its width was just over 1 kilometer, and it blocked a star for only about 0.3 of a second. A follow-up study published in December of 2012 reported another covering by a similar object, with a radius of about 530 meters. From these rare events, the team concluded that there are far fewer sub-kilometer Kuiper belt objects than scientists had earlier thought based on the numbers of larger bodies. More data came from NASA's New Horizons spacecraft, whose Venetia Burney student dust counter found more dust bits, even out to 55 astronomical units from the Sun, than current models expected. This shows that we still do not fully understand how small bits and dust act in this far-off area. Beyond the Kuiper belt lies the scattered disk, a region that overlaps with the Kuiper belt but stretches outward to more than 100 astronomical units from the Sun. Objects in the scattered disk follow very stretched and tilted paths. According to most models, both Kuiper belt objects and scattered disk objects first formed together in an early first belt. Later, Neptune's gravity sent some into steady paths, the Kuiper belt, and others into unsteady ones, the scattered disk. Because of their unsteady paths, many scientists believe that the scattered disk is the main home of short-period comets. These icy bodies sometimes get pushed into the inner solar system, where they first become centaurs and later turn into short-period comets. The Minor Planet Center, which keeps the official records of all trans-Neptunian objects, defines a Kuiper belt object as anything that stays strictly within the Kuiper belt's path zone. Anything beyond that is seen as a scattered object. In practice, though, many scientists freely use the term Kuiper belt object to describe almost any icy world in the outer solar system, even if its path has taken it far beyond the belt itself. This is why Eris, which is actually a scattered disk object and even heavier than Pluto, is often called a Kuiper belt object in talk. Because of this overlap, astronomers still do not fully agree on the exact meaning of the Kuiper belt. Then, there are the centaurs. These bodies are not usually seen as part of the Kuiper belt because they were thrown inward toward the giant planets rather than outward. Still, the Minor Planet Center groups both the centaurs and the scattered disk objects together as one wider family of scattered objects. During its long trip outward through the solar system, the planet Neptune is thought to have caught a wandering giant from the Kuiper belt, Triton. Triton is special because it is the only large moon in the whole solar system that circles its planet in a backward direction, meaning it moves the opposite way to Neptune's spin. This strange motion clearly shows that Triton was not born around Neptune. Unlike the great moons of Jupiter, Saturn, and Uranus, which likely formed naturally from spinning disks of gas and dust that surrounded their young parent planets, Triton was already a fully formed body before Neptune caught it. But catching such a large object is no simple job. For an object to be trapped by a planet's pull, it must somehow slow down during its meeting, otherwise it would just fly past and escape. One widely accepted idea is that Triton was once part of a twin pair, two bodies circling each other, when it came too close to Neptune. The giant planet may have flung one of the pair away into deep space while keeping Triton as its prize. This idea seems even more believable because many Kuiper Belt objects, or KBOs, are known to exist as twins. Triton is only about 14% bigger than Pluto, and both worlds share clear similarities. Views of their surfaces show that they are made of similar materials, including frozen methane and carbon monoxide. All this strongly suggests that Triton was once a Kuiper Belt object, until Neptune took it during its time of movement. Since the start of the 21st century, astronomers have found a growing family of large Kuiper Belt objects. Several of these new finds measure between 500 and 1,500 kilometers across, which is more than half the size of Pluto, whose width is about 2,370 kilometers. In the year 2002, scientists found Quaoar, a classical Kuiper Belt object over 1,200 kilometers wide. Just 3 years later, on the 29th of July 2005, two even larger objects, Makemake and Haumea, were announced. Others, such as Ixion, found in 2001, and Varuna, found in 2000, measure around 600 to 700 kilometers across. The discovery of so many Pluto-sized worlds made astronomers rethink Pluto's special place. These bodies not only match Pluto in size, but many also have moons of their own, and they are made of the same ices, such as methane and carbon monoxide. The situation repeated history. Just as the asteroid series was first called a planet until many other asteroids were found, Pluto now seemed to be one among many. The debate grew stronger with the discovery of Eris, a faraway body in the scattered disk, well beyond the Kuiper Belt. Eris turned out to be 27% heavier than Pluto. At first, it was even thought to be slightly bigger in size, though the New Horizons mission later showed that Pluto is a bit wider, even though it weighs less. Eris pushed the International Astronomical Union, or IAU, to make a clear rule for what makes a planet. Their new rule said that a true planet must clear the area around its path. Because Pluto shares its space with many other large bodies in the Kuiper Belt, it failed this test. In 2006, Pluto was officially changed to a dwarf planet, joining the very group of objects that had first questioned its special status. Astronomers now wonder just how many Kuiper Belt objects are big enough to be dwarf planets. Many possible ones have surprisingly low weights, showing that fewer fit the rule than once thought. Still, most experts agree that Orcus, Haumea, Quaoar, Makemake, and of course Pluto belong to this special group. Others have added more names such as Salacia, Mani, Aya, and Ixion. Among the trans-Neptunian objects, the six biggest, Eris, Pluto, Gong, Makemake, Haumea, and Quaoar, are all known to have moons. In fact, two of them have more than one. Larger Kuiper Belt objects are more likely to have moons than smaller ones, hinting at a different way of forming. Another interesting find is the high number of twin objects in the Kuiper Belt. About 11% of KBOs exist as pairs circling each other, the most famous being the Pluto-Charon pair. Study of this far-off area began on the 19th of January 2006, when NASA sent off the New Horizons spacecraft. After a 9.5-year trip, New Horizons flew past Pluto on the 14th of July 2015, giving the first close-up views of the dwarf planet and its moons. But the mission did not end there. Beyond Pluto, its goal was to explore even farther Kuiper Belt objects. In October 2014, the Hubble Space Telescope found 3 possible targets for the spacecraft, known simply as PT1, PT2, and PT3, short for Possible Target 1, 2, and 3. These objects were tiny, with estimated widths between 30 and 55 kilometers, far too small to be seen from Earth with ground telescopes. They circled the Sun at distances of 43 to 44 astronomical units, and mission planners worked out their chances of being reachable. PT1 at 100%, PT2 at only 7%, and PT3 at 97%. PT1, later named 2014 MU69, and later called Arakoth, became the chosen target. In late 2015, New Horizons changed its course to aim for this small, ancient world. On the 1st of January 2019, the spacecraft flew past Arakoth, showing it to be a strange contact twin. Two parts joined together like a snowman, about 32 kilometers long and 16 kilometers wide. Its surface looked a deep red, the color of organic matter changed by ages of space radiation. Although New Horizons still sends back data, no more missions are planned for now. Yet scientists are already thinking of what could come next: orbiters or landers for Pluto, or new trips to study Haumea and make up close. Haumea, in particular, interests researchers because it is the parent body of a crash-made family of objects, has 2 moons and even a ring. Engineers at Thales Alenia Space have studied how a spacecraft could be sent to circle Haumea within 10 to 20 years of launch. Alan Stern, the lead scientist of New Horizons, has even suggested missions that might first fly past Uranus or Neptune before continuing to new Kuiper Belt targets, bringing back the thrill of the Voyager flybys of the 1980s. The Kuiper Belt, once just an idea, is now a frontier full of discovery. Each new object found adds another part to the story of how the solar system was built and still changes, far beyond the path of Neptune. Scientists have thought about the faraway world Quaoar as a possible stopover or flyby target for a space probe meant to later explore the mysterious space between the stars, the vast area that lies between star systems. Quaoar happens to be near a special area called the heliospheric nose, which is the part of the Sun's protective bubble that faces into the flow of matter coming from interstellar space. Because of this, it would be a great stepping stone on the way out of the solar system. Pontus Brandt, a scientist at the Johns Hopkins Applied Physics Laboratory, and his team explored the idea of sending a deep space probe far beyond our solar system. Their plan was bold and imaginative. The spacecraft would first fly past the icy world Quaoar sometime in the decade of the 2030s. After that, it would continue its long journey outward, heading straight through the nose of the heliosphere, the protective bubble created by the Sun's influence, and then finally enter the vast emptiness of interstellar space. Quaoar itself has become one of the most fascinating objects in the outer solar system. It appears to have a very thin and fragile atmosphere made mostly of methane, which may be slowly escaping into space. Scientists also believe that Quaoar shows signs of cryovolcanism, a process similar to volcanic activity on Earth, except that instead of hot, molten rock, the eruptions involve frozen materials like water, ammonia, or methane ice. These icy volcanoes could reveal much about how such distant worlds evolve and change over time. The proposed mission would ride into space aboard NASA's powerful Space Launch System rocket, one of the largest rockets ever built. Once in space, the probe would perform a daring maneuver. It would swing around Jupiter, using the giant planet's gravity as a slingshot to gain extra speed. After this gravitational boost, the spacecraft could travel at an astonishing speed of about 30 kilometers per second, racing away from the Sun faster than almost any other human-made object. Some researchers have imagined going even further. Instead of simply flying past a Kuiper Belt object, what if a probe could actually orbit one? In a detailed study published in the year 2012, scientists calculated that 2 objects, named Ixion and Huya, might be the best candidates for such a mission. Their model suggested that if a spacecraft were launched toward Ixion in the year 2039, it could arrive after about 17 years of steady travel, a journey that would bring humanity face to face with one of the distant icy remnants of the early solar system. By the year 2006, astronomers had already found dusty, ring-like disks surrounding 9 stars beyond our Sun. These strange and beautiful structures are believed to be the counterparts of our own Kuiper Belt, the leftover debris from the formation of other planetary systems. Interestingly, these disks tend to fall into 2 distinct categories. Some are wide, extending more than 50 astronomical units from their stars, while others are narrow and compact, stretching only between 20 and 30 astronomical units, with edges that look surprisingly neat and sharply defined. Further research has shown that about 15 to 20% of stars similar to our Sun display an unusual warmth in the infrared part of the spectrum. This faint glow is a strong clue that dusty disks, much like the Kuiper Belt, surround them. Most of these debris disks are young, still filled with the energy and chaos of planetary formation. However, in January of the year 2006, the Hubble Space Telescope captured two remarkable images of much older systems, about 300 million years in age. Unlike their younger counterparts, these ancient disks had already settled into stable and enduring shapes. One of them was a broad, flat ring viewed from above, while the other appeared as a slender, shining belt seen edge-on against the darkness of space. Computer models of our own Kuiper belt suggest that it too was once very different. In its early days, billions of years ago, it might have resembled the delicate, shimmering rings now seen around young stars. Far to the south, in the constellation known as Centaurus, lies one of the most remarkable sights in the heavens, the brilliant system of Alpha Centauri. When you look up at it on a clear southern night, it may appear as a single shining star, but in truth it is a small family of three suns bound together by gravity. These three members are Rigil Kentaurus, also called Alpha Centauri A, Ptolemy, also called Alpha Centauri B, and the faint little companion Proxima Centauri, also called Alpha Centauri C. Among them, Proxima Centauri holds a special place in the story of the stars, for it is the closest star to our own Sun. It lies about 4 1/4 light-years away, or roughly 1 1/3 parsecs. The other two, Rigil Kentaurus and Ptolemy, are the closest bright stars that can be seen without any telescope, glowing together like a single golden gem. Rigil Kentaurus and Ptolemy are quite similar to our Sun, though each has its own personality. Rigil Kentaurus is a G-type star, warm, bright, and golden, while Ptolemy is a cooler K-type star with a slightly more orange tint. These two orbit one another, forming what astronomers call a binary system, Alpha Centauri AB. To the unaided eye on Earth, their light merges together so perfectly that they seem like one dazzling star. Their combined brightness is about magnitude -0.27, making them not only the brightest stars in the Centaurus constellation, but also the third brightest in the entire night sky, surpassed only by Sirius and Canopus. Together they form the nearest pair of stars to the Sun, only about 4 1/3 light-years away, a distance that light itself would take more than 4 years to cross. Rigil Kentaurus is a little larger and heavier than the Sun, with about 1 1/10 times its mass, and shining with about 1 1/2 times its brightness. Ptolemy is slightly smaller and dimmer, about 9/10 the mass of our Sun, and glows with less than half its light. The two stars circle around their shared centre of gravity once every 79 years, following a stretched-out oval-shaped orbit. At their closest, they are about 11 astronomical units apart, roughly the distance between the Sun and Saturn, and at their farthest, they drift apart to about 36 astronomical units, nearly the distance from the Sun to Pluto. Their faint companion, Proxima Centauri, is a small red dwarf star, a cool, dim ember of the universe, belonging to the M class of stars. It cannot be seen with the naked eye, but it is actually even nearer to us than the brighter pair, at about 4 1/4 light-years, or roughly 1 1/3 parsecs. Proxima orbits the main pair from an enormous distance, about 13,000 astronomical units away, or 1/5 of a light-year. That is more than 400 times the size of Neptune's orbit around the Sun. Despite its faintness, Proxima Centauri has gained much attention because it has at least 2 known planets. The first, called Proxima b, is roughly the same size as Earth and circles within the so-called habitable zone, where temperatures might allow liquid water to exist. Yet the star's flares and harsh radiation make it unlikely that life as we know it could survive there. The second planet, Proxima d, is smaller than Earth and orbits much closer to the star. There may even be a third world, Proxima c, which could be a mini Neptune orbiting farther out at about 1 1/2 astronomical units, though astronomers are still debating whether it truly exists. Interestingly, Rigil Kentaurus may also have a planet about the size of Saturn within its habitable zone, but its presence has not yet been confirmed. Ptolemy, however, has no verified planets of its own. The name Alpha Centauri has an old and noble history. It was given in the year 1603 by the German astronomer Johann Bayer, who catalogued stars using Greek letters and the names of their constellations. Centaurus, the constellation that holds this system, was named after the legendary centaur of Greek mythology, a creature half man and half horse. According to ancient tales, the hero Heracles once wounded this centaur by accident, and after his death, placed him among the stars. In the sky, Alpha Centauri marks the bright front hoof of this celestial being. The name Rigil Centaurus is a Latinized version of the Old Arabic phrase Rigil al-Kintarus, meaning the foot of the centaur. The word Kintarus itself is derived from the Greek word Kentauros. Sometimes the star is simply called Rigil Kent, or even Rigil, though the shorter name can be confusing since another star, Rigel in Orion, shares it. The other bright member, Ptolemy, also has Arabic roots. It likely comes from az-Zalaman, meaning the two ostriches. The name originally referred to a pair of stars in the constellation Sagittarius, but over time it became associated with Alpha Centauri. The name gained further fame in Europe after the Dutch scholar Jacob Golius used it in his Latin translation of the writings of Alfagani in the year 1669. Proxima Centauri, the faint red dwarf, was discovered much later, in the year 1915, by the Scottish astronomer Robert Innes. While observing Alpha Centauri, he noticed a tiny star that seemed to share its motion across the sky. After careful study, he realized this faint star was even closer to us than the main pair. He named it Proxima Centaurus, Latin for the nearest star of Centaurus. Over time, the simpler name Proxima Centauri became standard and was officially adopted by the International Astronomical Union. In the year 2016, the International Astronomical Union decided that each star in multiple systems should have its own unique name. That same year, the names Rigil Centaurus for Alpha Centauri A and Proxima Centauri for Alpha Centauri C were formally approved. 2 years later, in August of the year 2018, the name Ptolemy was officially confirmed for Alpha Centauri B. Throughout history, the system has been known by many other names. In the 19th century, the American skywriter Elijah Burritt called it Bungula, though no one is quite sure where that name came from. It might have been inspired by the Greek letter beta and the Latin word ungula, meaning hoof. Different cultures across the world have their own stories about this star. In ancient Chinese astronomy, Alpha Centauri and Epsilon Centauri formed an asterism called Nanmen, or the Southern Gate. Thus, Alpha Centauri was known as Nanmen-er, the second star of the Southern Gate. Among the indigenous Burong people of northwestern Victoria and Australia, Alpha Centauri and Beta Centauri were known as Bermbamel, two heroic brothers who hunted and defeated Chingal, the emu, represented by the dark Coalsack Nebula nearby. In another Aboriginal language, Wotjobaluk, the pair were called Bram Bram Bult. Seen with the unaided eye, Alpha Centauri A and B look like a single point of golden light, the brightest jewel in the southern sky. But through binoculars or a small telescope, their true nature is revealed. Two suns locked in a graceful cosmic dance. Over a period of about 80 years, their apparent closeness slowly changes. At times, they seem almost to touch, separated by only 2 arcseconds. At other times, they drift apart by as much as 22 arcseconds. To give a sense of scale, the human eye can normally distinguish details down to about 60 arcseconds, so a modest telescope easily separates them. For people living south of about 29 degrees south latitude, Alpha Centauri never goes below the horizon. It is a circumpolar star, always visible in the night sky. But for those living north of about 29 degrees north latitude, the star never rises at all. Between these areas, from about 29 degrees north down to the equator, the star can just be seen close to the southern horizon for a short time each year when it reaches its highest point. This is true for cities such as Hermosillo and Chihuahua in Mexico, Galveston in Texas, Ocala in Florida, and the island of Lanzarote in Spain's Canary Islands. Each year, Alpha Centauri is highest in the sky at midnight on the 24th of April and at 9 o'clock in the evening on the 8th of June. Not far away in the sky, Proxima Centauri, the faint third member of the Alpha Centauri system, lies about 2.2 degrees to the southwest. This distance is about 4 times wider than the Moon's apparent size. Proxima Centauri appears as a dim, deep red star with a brightness of magnitude 11.1. Because it is faint and lies in a fairly empty area of the sky, one needs a medium or large telescope to see it. Listed as V645 Centauri in the General Catalogue of Variable Stars, version 4.2, it belongs to a group of stars called flare stars. These are unstable stars that can suddenly grow brighter by up to 0.6 magnitude within minutes before dimming again. Amateur and professional astronomers often watch Proxima with optical or radio telescopes, hoping to see one of these sudden flares. In August of the year 2015, Proxima produced its largest known flares, briefly shining 8.3 times brighter than usual on the 13th of August. In the blue part of the spectrum, Alpha Centauri's fame goes back to ancient times. The great astronomer Claudius Ptolemy included it in his star catalogue of the 2nd century, known as the Almagest. He wrote down its ecliptic coordinates, though surviving copies of his work differ slightly, some giving its latitude as 44 degrees 10 minutes south, others as 41 degrees 10 minutes south. Today, its ecliptic latitude is about 43.5 degrees south, changed slightly since Ptolemy's time because of the star's slow motion. In Ptolemy's time, Alpha Centauri could still be seen from Alexandria in Egypt at latitude 31 degrees north. Now, because of the slow wobble of Earth's axis known as precession, the star's position has shifted, and it can no longer be seen from there. In the year 1592, the English explorer Robert Hughes introduced Alpha Centauri to European scholars in his book Tractatus de Globis. He described it along with Canopus and Achernar as one of only 3 first-magnitude stars that could never be seen from England. He placed Alpha Centauri in the right foot of the Centaur. A century later, in December of 1689, the French astronomer Jean Richaud, while observing a comet from the Indian city of Puducherry, discovered that Alpha Centauri was not 1 star but 2. This made Alpha Centauri only the 3rd known double star, after Mizar in Ursa Major and Acrux in the Southern Cross. The large motion of the system, its slow but visible drift across the sky, was first noticed by Manuel John Johnson, observing from the island of St. Helena. He sent his findings to Thomas Henderson at the Royal Observatory in Cape Town, South Africa. Henderson then made very careful measurements of the parallax of Alpha Centauri between April of 1832 and May of 1833. At first, he doubted his results, thinking they were too large to be correct, and delayed publishing them. Finally, in 1839, he released his work after Friedrich Bessel had published the parallax of 61 Cygni in 1838. Because of this, Alpha Centauri is sometimes called the 2nd star whose distance was measured, even though Henderson was actually first. Today, we know Alpha Centauri is about 4.396 light-years away, or roughly 41,590,000,000,000 kilometers. In 1834, John Herschel made the first detailed measurements of the system, and in the early 20th century, astronomers began using photographic plates for more accuracy. By the year 1926, William Stephen Finson had already calculated orbital details close to the ones accepted today, letting astronomers predict the star's positions with great accuracy. Later, in the year 2002, Deep-Orbit further improved these orbital calculations. The 3rd star, Proxima Centauri, was discovered much later in 1915 by the Scottish astronomer Robert Thorburn Ayton Innes. By comparing photographs taken at different times, he noticed that this faint red star showed the same large motion and parallax as Alpha Centauri A and B, but was slightly closer. From this, he concluded that Proxima was truly part of the system, and the nearest star to Earth known at that time. Alpha Centauri, the closest star system to our Sun, may lie inside a region of space called the G-cloud, which is part of the larger local bubble of interstellar gas. The nearest known stellar system to Alpha Centauri is a pair of faint brown dwarfs known as Lumen 16. This unusual double system lies at a distance of about 3 6/10 light-years, or a little more than 1 parsec, from Alpha Centauri. All of the stars in Alpha Centauri show what astronomers call proper motion. This means that, over many years and centuries, their positions slowly change against the background of other stars in the sky. Ancient astronomers, who did not know about proper motion, believed that the stars were fixed forever on a giant crystal sphere surrounding Earth, an idea described by the philosopher Aristotle. It was not until the year 1718 that the English astronomer Edmund Halley noticed that some bright stars had clearly moved since the days of the ancient Greek star lists. A little more than a century later, in the 1830s, the Scottish astronomer Thomas Henderson studied Alpha Centauri using a large mural circle for precise measurements. He discovered the true distance to the star system, making Alpha Centauri the first star, other than the Sun, to have its distance correctly measured. Henderson also noticed that this system had a very strong motion. To confirm this, he compared his results with earlier measurements made by the French astronomer Nicolas Louis de Lacaille in the years 1751 to 1752. The difference between the two sets of data proved that Alpha Centauri was indeed moving quickly across the sky. Modern calculations show that the combined centre of mass of Alpha Centauri A and B moves across the sky at about 3,620 milliseconds per year toward the west and 694 milliseconds per year toward the north. This gives an overall motion of about 3,686 milliseconds per year in a direction about 11 degrees north of west. In simpler terms, the pair moves by about 6 arc-minutes every century, or a little more than 1 degree every 1,000 years. In terms of real speed through space, Alpha Centauri AB travels at about 23 kilometers per second to the west and about 4 4/10 kilometers per second to the north. Spectroscopic studies also show that the system is moving toward our solar system at about 22 4/10 kilometers per second. Altogether, Alpha Centauri is moving through space at a total speed of about 32 4/10 kilometers per second compared to the Sun. This speed is close to the average for nearby stars, because Alpha Centauri AB lies almost exactly in the same plane as the Milky Way when seen from Earth. Many distant stars can be seen directly behind it. This alignment sometimes creates special chances for astronomy. For example, in early May of the year 2028, Alpha Centauri A will pass in front of a distant red star. There is about a 45% chance that the light of that distant star will be bent into a bright ring of light, called an Einstein ring, by the gravity of Alpha Centauri. Other such alignments will happen in the future, allowing scientists to improve motion measurements and perhaps even find planets around these stars. Over the coming thousands of years, Alpha Centauri will keep changing its position in the sky. Around the year 6200 of the Common Era, it will appear in a rare and beautiful close meeting with Beta Centauri, forming a bright double star in the southern sky. Later, it will move northward past the famous Southern Cross and slowly climb toward the celestial equator. By around the year 26,700, in the present-day constellation of Hydra, Alpha Centauri will come closer to our solar system than ever before, just about 9/10 of a parsec, or roughly 2 9/10 light-years away. Some newer calculations place this closest approach a few centuries later, around the year 27,000. At that time, Alpha Centauri will shine even brighter than it does today, with a magnitude of about -0.86, almost as bright as Canopus. Yet even then, it will not outshine Sirius, which will remain the brightest star in Earth's sky, apart from the Sun, for the next 60,000 years and more, keeping that title for about 210,000 years into the future. Alpha Centauri is not a single star but a triple system. Its two brightest members, Alpha Centauri A and Alpha Centauri B, form a close double star that orbit around a shared centre of mass. Astronomers often call this pair Alpha Centauri AB, and sometimes write it as AX-B. The faint red dwarf Proxima Centauri, also called Alpha Centauri C, orbits much farther out, making the system a true trio. Because Proxima is almost equally distant from Alpha Centauri A and B, scientists sometimes treat the inner double pair as if it were a single body when studying Proxima's orbit. Alpha Centauri A and B take almost exactly 79 3/4 years to finish one orbit around each other. Their orbit is not a perfect circle but an oval shape, with a moderate stretch of about 0.52. When they are closest to each other, called periastron, the two stars are about 11 2/10 astronomical units apart, about the same distance between the Sun and Saturn. When they are farthest apart, called a pastron, they are about 35 6/10 astronomical units apart, similar to the distance between the Sun and Pluto. The last periastron happened in August of the year 1955, and the next will be in May of the year 2035. Their last apastron occurred in May of the year 1995, and the next will happen in the year 2075. From Earth, we see the star's orbit as it appears in the sky, so their distance and position angle keep changing. For example, in the year 2019 the stars were about 4 9200 arc-seconds apart, at a position angle of 337 1/10 degrees. By the year 2020, the distance had grown to about 5 4900 arc-seconds at a position angle of 345 3/10 degrees. Their closest recent approach was in February of the year 2016, when they were only 4 arcseconds apart at a position angle of 300 degrees. At their widest, Alpha Centauri A and B appear about 22 arcseconds apart, while at their narrowest, they are only about 1 7/10 arcseconds apart. The last time they were farthest apart was in February of the year 1976, and the next time will be in January of the year 2056. Farther out, Proxima Centauri is about 13,000 astronomical units away, or about 2/10 of a light year from the main pair. This is about 5% of the distance between Alpha Centauri AB and the Sun. For many years, scientists were not sure if Proxima was truly held by gravity to Alpha Centauri AB, or if it was just passing nearby. In the year 2017, accurate measurements of Proxima's motion finally proved that it is truly part of the system. Proxima Centauri's orbit around the central pair is huge and very stretched out. Its orbital period is about 511,000 years, give or take several tens of thousands. When it is closest, Proxima comes to about 4,100 astronomical units from Alpha Centauri AB, and when it's farthest, it goes out to about 12,300 astronomical units. This makes its orbit much more stretched than Mercury's in our solar system, giving Proxima a very long and uneven path around its brighter companions. Scientists have studied the Alpha Centauri system using many methods, including studying vibrations inside the stars, astroseismology, measuring surface activity, and studying how the stars spin, gyrochronology. All of these different methods lead to the same result. Alpha Centauri is about the same age as the Sun, or maybe a little older. When scientists used detailed data to study the star's vibrations, they found different possible ages. Some studies gave about 4.85 billion years with a margin of 500 million years, others gave 5 billion years with the same margin, and others found 5.2 billion years with a margin of almost 2 billion years. Some results suggested 6.4 billion years, while the most accurate gave 6.52 billion years, with only 300 million years of uncertainty. Looking at surface activity, basically the behavior of calcium emissions from the stars, gave an age of around 4.4 billion years, though with a large uncertainty of about 2.1 billion years. Studying the star's rotation, gyrochronology, gave an age of about 5 billion years with a margin of only 300 million years. Models of how stars change over time also support that Alpha Centauri A and B are slightly older than the Sun, somewhere between 5 and 6 billion years old. By studying how the two main stars move, scientists found that their total mass is about twice that of the Sun. Separately, Alpha Centauri A has about 1.08 times the Sun's mass, and Alpha Centauri B has about 0.91 times the Sun's mass. Some studies suggest slightly different numbers, A with 1.14 solar masses and B with 0.92, giving a total of about 2.06 solar masses. In terms of brightness, Alpha Centauri A shines with an absolute magnitude of about plus 4.38, while Alpha Centauri B has a magnitude of plus 5.71. Alpha Centauri A, also called Rigil Kentaurus, is the brighter and heavier of the two. It is a yellow star, very similar to our Sun, and is a G2 main sequence star. It is about 10% heavier than the Sun and about 22% larger. In the night sky, it is one of the brightest stars, ranking 4th overall, with an apparent magnitude just above 0. It's only a bit dimmer than Arcturus, which has a magnitude slightly below 0. Like the Sun, Alpha Centauri A shows magnetic activity such as dark spots and outer layer changes linked to its rotation. But since the year 2005, its activity has entered a very quiet stage, possibly like the Sun's Maunder minimum that happened centuries ago. Some scientists think this is part of a very long activity cycle, and that the star may slowly be becoming more active again. Alpha Centauri B, also called Ptolemy, is the smaller and slightly cooler star. It is an orange K1 main sequence star with about 90% of the Sun's mass, and a size that is 14% smaller. Though it is less bright in visible light than Alpha Centauri A, it gives off more energy in X-rays. Its brightness changes more over short periods, and at least one flare has been seen. Alpha Centauri B is more magnetically active than Alpha Centauri A, showing an activity cycle of about 8.2 years compared with the Sun's 11-year cycle. Later observations found a slightly shorter cycle of 7.8 years. Its brightness in the sky, with a magnitude of plus 1.35, makes it just a little dimmer than the star Mimosa. The third star, Alpha Centauri C, better known as Proxima Centauri, is a tiny red dwarf. It belongs to the M6 spectral type and shines very faintly with an absolute magnitude of plus 15.6, more than 20,000 times dimmer than the Sun. It has only about 12% of the Sun's mass. Even though it is the closest star to us after the Sun, Proxima is too dim to be seen without a telescope. So far, scientists have confirmed 2 planets in the Alpha Centauri system, both orbiting Proxima Centauri. Many more planets have been suggested around all 3 stars, but most of those claims have not been proven. In the year 2021, a possible planet called Candidate 1 was found around Alpha Centauri A. It seemed to orbit at about 1.1 astronomical units, about the same distance as Earth from the Sun, with a period of about 1 year. Its size was thought to be between that of Neptune and half that of Saturn. However, it might not be a planet but instead a disk of dust or an error in the observation. Later studies ruled out the chance that it was just a background star. If confirmed, this planet would likely be named Alpha Centauri AB. The James Webb Space Telescope has been given the task of looking for planets in the Alpha Centauri system. Its first detailed observations in July of the year 2023 did not find anything, but more searches were planned for March of the year 2024. Based on its ability, Webb is expected to find planets as small as 3 to 5 times the size of Earth, at distances between 0.5 and 3 astronomical units from Alpha Centauri A. In August of 2024, Webb saw a faint light source about 2 astronomical units away from Alpha Centauri A. This could be the same possible planet reported in 2021. The object is unlikely to be a mistake, but more observations are needed to confirm it as a planet. If it truly is one, it would probably weigh between 90 and 150 times the mass of Earth, be about the size of Jupiter, and have a very cold temperature of about minus 48 degrees Celsius. The first major claim of a planet around Alpha Centauri B came in the year 2012, when scientists thought they had found a planet about the size of Earth orbiting every 3.2 days. However, this was proven wrong in 2015 when the signal was shown to be caused by the way the data was handled. Another search using the Hubble Space Telescope between 2013 and 2014 found a possible transit that might belong to another small planet around Alpha Centauri B. This object might be smaller than Earth and could go around the star every 12 to 20 days. If it exists, it would likely be covered in lakes of molten lava and far too hot to support life. But this finding too remains unconfirmed. The most hopeful planet in the system is still Proxima Centauri B, discovered in 2016 by the European Southern Observatory. This world is just a bit heavier than Earth and moves very close to Proxima Centauri, inside its habitable zone, where liquid water could exist. The discovery of a possible planet named Proxima Centauri C was first made public in the year 2020. This strange world could either be a super-Earth, which is a rocky planet larger than Earth, or a mini-Neptune, a smaller version of the icy giant Neptune. Scientists estimated its mass to be around 7 times that of Earth. It seemed to orbit its main star, Proxima Centauri, at a distance of about 1.5 astronomical units, which means about 1.5 times the distance between Earth and the Sun. Completing one full orbit was thought to take nearly 1,928 days, just over 5 years. In June of 2020, scientists even believed they might have taken a direct picture of this planet, and some thought it could be surrounded by a large ring system. However, excitement soon turned to doubt. By the year 2022, new research questioned whether Proxima C even existed at all. And as of the year 2025, the evidence still remains unclear. Observations made with an advanced tool called the NURBS spectrograph failed to confirm the planet, though they did find a faint signal with a similar orbital rhythm, suggesting that something might still be there, but not as heavy as once thought. Another study in the year 2020 tried to better measure the mass of the already known planet Proxima b. This study ruled out the presence of any other planets larger than about 6/10 the mass of Earth, with short orbital periods of less than 50 days. But to their surprise, the scientists did find a very weak radial velocity signal, repeating every 5.15 days. This suggested the presence of a tiny planet with a mass of less than 1/3 that of Earth. This new world, later named Proxima Centauri d, was first announced in the year 2022 and officially confirmed in the year 2025. The possibility of other planets in the Alpha Centauri system has long interested scientists. These could be moving around either Alpha Centauri A or Alpha Centauri B individually, or maybe even both stars in a wide orbit. Because Alpha Centauri A and B are so similar to our Sun in age, makeup and brightness, planet hunting teams have been especially eager to search these stars for Earth-like worlds. Using advanced methods like radial velocity tracking and star transit observations, scientists have carefully studied both stars. So far, no proof has been found for large gas giants or brown dwarfs orbiting either of them. In the year 2009, computer models suggested that a planet could have formed within the habitable zone of Alpha Centauri B. This zone, where liquid water could exist on a planet's surface, stretches from about half an astronomical unit to nearly 9/10 of an astronomical unit from the star. Some models even suggested that if Alpha Centauri A and B had originally been farther apart and later moved closer, something possible if they were born in a crowded star cluster, then the conditions for forming planets could have been even better. Around Alpha Centauri A, planets might form slightly farther out, because its stronger gravity would allow stable orbits at greater distances. The fact that neither Alpha Centauri A nor B has close orbiting gas giants or brown dwarfs is actually good news. Without these huge planets disturbing their systems, the chances of smaller, rocky, Earth-like planets forming is thought to be much higher. Theoretical studies suggest that, with better sensitivity, scientists might one day find a planet about 1.8 times the mass of Earth within Alpha Centauri B's habitable zone. Accurate measurements of Alpha Centauri B, made using the very precise HARP spectrograph, short for High Accuracy Radial Velocity Planet Searcher, should have been able to find planets with masses of about 4 times that of Earth and orbital periods of about 200 days, exactly the kind of worlds that could be in the habitable zone. Yet no such planets were found. Even so, scientists believe there is still a very good chance, around 75%, that at least one Earth-like planet could exist somewhere within the Alpha Centauri system. Current detection limits suggest that planets as small as about 53 Earth masses could be seen around Alpha Centauri A, about 8 Earth masses around Alpha Centauri B, and less than half an Earth mass around Proxima Centauri. Early computer models once strongly predicted that Earth-like planets should exist around both Alpha Centauri A and Alpha Centauri B. More recent and detailed simulations, however, show that the constant pull between these two stars makes planet formation much harder than first thought. Yet despite these challenges, many scientists believe Alpha Centauri is still one of the best possible places to look for alien life beyond our solar system. Its stars are so much like our Sun, and their long-term orbital stability could easily provide the calm, steady conditions needed for life to grow. Looking at our own solar system for comparison, scientists once thought that the giant planets Jupiter and Saturn had played a key role in guiding comets into the inner system, bringing valuable water and ice to the young Earth and its nearby planets. But later, more careful measurements of the deuterium to hydrogen ratio in several comets, including Halley, Hyakutake, Hale-Bopp, T7 of 2002, and Tuttle, showed that their water had nearly twice the ratio found in Earth's oceans. This discovery suggested that comets brought less than 1/10 of Earth's water, with most of it coming from other sources. In a similar way, Proxima Centauri might have affected the early planet-forming disk of the Alpha Centauri system, adding icy material to the region. However, this idea could be questioned if Alpha Centauri A or B happened to have hidden gas giants that stirred their own comet groups, just as Jupiter and Saturn are thought to have done in our solar system. It is also likely that Alpha Centauri, like our own Sun, has a faraway Oort cloud filled with icy objects. From time to time, passing stars or gravitational pulls from giant planets can disturb these clouds, sending frozen comets falling inward toward their stars. The same thing could one day happen in our solar system if Alpha Centauri or another nearby star passes close enough, shaking our own Oort cloud and filling the skies with a new wave of comets. Between the years 2007 and 2012, scientists carefully watched Alpha Centauri A and B and noticed something strange. In the mid to far infrared range, especially around the wavelength of 24 micrometers, they found a small extra amount of radiation. This faint glow could mean that there is a thin ring of dust, or even a very light disk of debris circling the stars. The total amount of material, however, would be very small, only between 1/10 millionth and 1 millionth of the Moon's mass. That is roughly 10 to 100 times more than the mass of the zodiacal cloud, which is the thin dust spread throughout our own solar system. If such dusty disks really exist, then around Alpha Centauri A it would likely stay stable only up to about 2 8/10 astronomical units from the star, while Alpha Centauri B's disk would be stable up to about 2 5/10 astronomical units. This means that the entire disk around star A would stay inside the so-called frost line, where water and other light materials cannot freeze. In contrast, the disk around star B would stretch just a little beyond that icy border. Some scientists have even suggested that material from such disks might not stay there. Instead, it could be shared with the far outer parts of our own solar system, meaning that dust or debris from Alpha Centauri could, in theory, drift toward us, and the same the other way around. If this were proven true, it would show that stars and planetary systems across the galaxy might be linked by a vast network of shared material. The night sky as seen from Alpha Centauri A or B would look surprisingly familiar to us on Earth, but with one big difference. The brightest star in the constellation Centaurus, which from Earth is Alpha Centauri itself, would no longer be there. From that viewpoint, the Sun would instead take its place. To someone near Alpha Centauri, the Sun would shine as a white star of magnitude plus 0.5, about the same brightness that Betelgeuse appears to us here on Earth. It would be seen in the constellation Cassiopeia, in the eastern part of the sky, very close to the Heart Nebula. There, the familiar W shape of Cassiopeia's stars would look a bit different, bent into something more like /W. Other well-known stars would also change their places in striking ways. Sirius, the brightest star in Earth's night sky, would still hold that title when seen from Alpha Centauri. At a distance of about 9 2/10 light years, it would shine with a magnitude of -1.2. But instead of being in Canis Major, it would appear in the constellation Orion, less than a single degree away from Betelgeuse. Procyon, another bright nearby star, would also change its position and would seem to outshine Pollux in the constellation Gemini. If there were an Earth-like planet moving around Alpha Centauri A at about 1 1/4 astronomical units from its star, a distance where the planet would take a little over 1 1/3 years to complete one orbit, it would receive light very similar to what Earth gets from the Sun. From this planet's sky, Alpha Centauri B would appear as a shining second star. Though much dimmer than the main one, it would still glow hundreds to thousands of times brighter than the full moon looks to us on Earth. The same would also be true. A planet moving around Alpha Centauri B at about 7/10 of an astronomical unit would see Alpha Centauri A as a brilliant companion star, shining far brighter than the moon in our night sky. Proxima Centauri, the third and smallest star in the Alpha Centauri family, would not look very remarkable if seen from planets orbiting the larger stars of the system. Most of the time it would shine only faintly, appearing as a small dim star of about magnitude 4 1/2. During its closest approach, an event known as periastron, it would glow just a little brighter, reaching about magnitude 2 6/10. Even then, it would still be a modest spark compared to the brilliance of its stellar companions. Because Alpha Centauri lies so close to our own solar system, astronomers have long dreamed of visiting it one day. It has often been imagined as the first stop for humanity's voyages beyond the Sun's family of planets. But even though it is the nearest star system to Earth, it is still unimaginably far away. If we were to send a spacecraft using the engines and fuels we have today, the journey would last for many thousands of years, far longer than any human lifetime or even the span of civilization itself. However, scientists have proposed bold new ideas that could change this. One such idea is nuclear pulse propulsion, where a spacecraft would move forward by a series of tiny controlled nuclear explosions behind it, pushing it faster and faster. Another concept involves laser-driven light sails, enormous, mirror-like sheets pushed by beams of powerful lasers from Earth. This is the idea behind the Breakthrough Starshot project, which aims to send tiny, lightweight probes to Alpha Centauri at incredible speeds. With such advanced technology, the trip that would normally take thousands of years could be reduced to only about 20 years. The dream is to send these miniature probes racing past the Alpha Centauri system to take close-up pictures of its stars and any planets that might orbit them. One of the most exciting targets would be Proxima Centauri B, a planet discovered in August of the year 2016 by astronomers at the European Southern Observatory. This world orbits within the habitable zone of its parent star, where temperatures might allow liquid water to exist, making it one of the most promising nearby places to search for life beyond Earth. Even NASA once explored the idea of such a journey. In the year 2017, the agency suggested launching a spacecraft toward Alpha Centauri in the year 2069 as a tribute to the 100th anniversary of the historic Apollo 11 moon landing of 1969. According to this daring plan, if the probe could travel at 1/10 the speed of light, about 108 million kilometers per hour, it would arrive at Alpha Centauri in the year 2113, 44 years after its launch. The first messages from this interstellar traveller would then take another 4 years to reach Earth, finally arriving in the year 2117. Sadly, after the proposal was made public, it never advanced beyond the idea stage. Funding was not provided, and the plan remained only a vision, a glimpse of what humanity might one day achieve when technology finally catches up with our dreams of reaching the stars. At the very heart of our Milky Way galaxy lies something truly remarkable, a hidden and incredibly powerful giant known as Sagittarius A star, a supermassive black hole. This strange and invisible object cannot be seen with the human eye, yet its enormous gravity quietly rules the center of our galaxy. From Earth, Sagittarius A star appears near the border between the constellations Sagittarius and Scorpius, only a few degrees south of the ecliptic, the path the sun follows through the sky. It also lies close to the glittering butterfly cluster and the bright star Lambda Scorpii. Although no light escapes from the black hole itself, it reveals its presence through strong radio waves, which astronomers can detect using powerful radio telescopes. A historic moment arrived on the 12th day of May in the year 2022, when the Event Horizon Telescope collaboration released the first ever image of Sagittarius A star. This was a monumental achievement in human exploration of the universe. The picture was created from data collected 5 years earlier, in 2017, proving beyond any doubt that a supermassive black hole truly lurks at the center of our Milky Way. It became only the second direct image of a black hole ever taken in history, following the earlier photo of the black hole in the galaxy M87. Achieving this incredible feat took half a decade of detailed work by hundreds of scientists who combined signals from 8 radio observatories across 6 different sites on Earth. They used a brilliant technique called aperture synthesis, which allowed them to create an image with incredible precision. Despite the fact that the radio emissions from the black hole's surroundings constantly changed from minute to minute, from this painstaking effort, astronomers found that Sagittarius A star appears to have an angular size of about 51.8 microarc seconds, with a small uncertainty of about 2.3 microarc seconds. Even though that angle is unimaginably tiny, it translates into an actual diameter of roughly 51,800,000 kilometers, or about 32,200,000 miles, because the black hole lies around 26,000 light-years away from Earth. To imagine that size, think of how the Earth orbits the Sun at a distance of about 150 million kilometers, while Mercury, the innermost planet, comes as close as 46 million kilometers. Sagittarius A star is also drifting slowly through space, moving about negative 2.7 milliseconds per year in right ascension and negative 5.6 milliseconds per year in declination. Careful measurements of its powerful gravity have provided some of the most precise tests ever made of Einstein's general theory of relativity, and every result so far has matched his predictions exactly. In the year 2019, astronomers made another breakthrough with help from NASA's SOFIA aircraft, which carried a special instrument called the High-Resolution Airborne Wideband Camera Plus. Their observations revealed that magnetic fields play a major role near the black hole. These invisible forces twist and shape the glowing ring of superheated gas and dust swirling around Sagittarius A star, where temperatures vary from nearly minus 280 degrees Fahrenheit, about minus 173 degrees Celsius, to more than 17,500 degrees Fahrenheit, about 10,000 degrees Celsius. These magnetic fields not only guide matter into orbit around the black hole, but also help to keep its overall activity surprisingly calm, despite its tremendous power. We cannot see Sagittarius A star with our eyes because the view toward it is blocked by thick clouds of gas and dust that fill the central region of the Milky Way. These clouds absorb and scatter almost all visible light, dimming it by about 25 magnitudes, which means the black hole's light is around 10 million times fainter than it would otherwise appear. The first hint of its existence came in April of 1933, when Carl Jansky, one of the founders of radio astronomy, picked up mysterious radio waves coming from the direction of Sagittarius, the region where the galactic centre lies. Later, Jack Piddington and Harry Minette in Sydney discovered a strong and compact radio source in the same area. As technology improved and larger telescopes were built, astronomers confirmed that this powerful radio signal marked the very core of our galaxy. Closer investigation revealed that the region known as Sagittarius A was not just a single object, but a crowded cluster of overlapping sources. The brightest and most concentrated part, what we now call Sagittarius A star, was identified in mid-February of 1974 by Bruce Balick and Robert L. Brown at the National Radio Astronomy Observatory. A few years later, in 1980, Brown named it A star, using the star symbol like the asterisk that marks excited states in atomic physics. By the 1980s, growing evidence pointed to Sagittarius A star being a black hole. Then, in 1994, a team from Berkeley, including Charles H. Townes, a Nobel Prize-winning scientist, and Reinhard Genzel, who would later receive the Nobel Prize himself, used advanced infrared and submillimeter instruments to estimate that its mass was around 3 million times the mass of our Sun. A major leap in our understanding came in mid-October of 2002, when Reinhard Genzel and his international team tracked the movement of a nearby star named S2 for an entire 10 years. The star's orbit showed clearly that the central object could not be a collection of ordinary stars or exotic remnants. It had to be a single, supermassive black hole. These observations, made in near-infrared light that can pierce through dust, revealed that Sagittarius A star contains about 4,100,000 times the mass of the Sun, all packed into a space only 17 light-hours wide. To picture that, it means its Schwarzschild radius, or the point of no return beyond which nothing can escape, is just about 12 million kilometers, roughly 0.08 astronomical units. Knowing the exact distance to the center of our galaxy is very important for mapping the universe. Astronomers now estimate it to be around 8,000 parsecs, or roughly 30,000 light-years away. In November of 2004, scientists found something even more intriguing. A possible intermediate mass black hole about 1,300 times the mass of the Sun, located just 3 light-years from Sagittarius A star inside a small cluster of 7 stars. This discovery may help explain how supermassive black holes like Sagittarius A star grow over time. By merging with smaller black holes and consuming the stars that wander too close to their immense gravitational pull. After 16 years of watching stars move around Sagittarius A star, a team led by Stephen Gillison figured out that its mass is about 4,300,000 times the mass of our Sun. Their findings, shared in 2009, gave some of the strongest proof yet that supermassive black holes truly exist. Genzel himself said that the motions of the stars were proof beyond any reasonable doubt. Although it is often calm, Sagittarius A star sometimes shows sudden bursts of activity. On the 5th day of January in 2015, NASA noticed an X-ray flare that was 400 times brighter than normal, probably caused by an asteroid being torn apart or by twisting magnetic fields in the gas falling toward it. On the 13th day of May in 2019, astronomers saw another flare, 75 times brighter than usual, possibly because a nearby object fell into the black hole. And as recently as June of 2023, scientists found strange radio threads around Sagittarius A star, making this galactic center even more mysterious. Another important discovery happened on the 31st day of October in 2018, when astronomers confirmed with certainty that Sagittarius A star is a supermassive black hole. Using the gravity interferometer along with the 4 large telescopes of the Very Large Telescope in Chile, scientists built a virtual telescope as wide as 130 meters, or about 430 feet. This huge virtual lens let them see clumps of gas spinning around the black hole at almost 30% of the speed of light, a stunning confirmation of the incredible power at the center of our galaxy. Astronomers also saw 3 very bright flashes caused by highly energetic electrons moving dangerously close to the black hole. These flares behaved exactly as scientists' models had expected, showing the paths of hotspots orbiting a black hole with a mass of about 4 million suns. Scientists think these bright bursts come from strong magnetic activity in the hot gas swirling near Sagittarius A star, offering a rare look at a cosmic storm far beyond our direct sight. Earlier that year, in July of 2018, another amazing event was seen. A star called S2, orbiting Sagittarius A star, was recorded moving at an incredible 7,650 kilometers per second, about 17.1 million miles per hour, which is around 2.5% of the speed of light. This happened when the star was at its closest point to the black hole called the pericenter in May of the same year. At that time, S2 was about 120 astronomical units away, roughly 18 billion kilometers or 11 billion miles, about 1,400 times the Schwarzschild radius of the black hole. At this close range, Einstein's theory of general relativity predicted that the star's light would be stretched by gravity, adding to the normal stretching caused by its high speed. Remarkably, this effect was seen and matched Einstein's predictions within 10%, giving another strong piece of proof for relativity. Interestingly, the radio waves coming from Sagittarius A star do not come directly from the black hole itself. Instead, they come from a bright area around it, near its edge. This could be part of the spinning disk of matter or a fast stream of gas being shot out from it. If the radio waves came exactly from the black hole, gravity would bend the light into a ring shape. According to general relativity, this ring would be about 5.2 times the Schwarzschild radius of the black hole, or around 52 microarc seconds. Observations show that Sagittarius A star looks almost this size, about 50 microarc seconds, while the black hole itself seems to be about 20 microarc seconds across. Lower quality images show that the radio source around Sagittarius A star looks smooth and even. Some other gravity theories could create images that look similar to those from general relativity, but computer models show that the smooth shape and small size fit what we expect from a black hole, confirming that Sagittarius A star is indeed a supermassive black hole. Scientists have measured the mass of Sagittarius A star in many ways. Two groups, one from Germany and one from the United States, carefully tracked the orbits of stars near the black hole. Using Kepler's laws, they estimated the mass inside these orbits. The German group calculated about 4.31 million suns, with a margin of error of plus or minus 380,000 suns. The American group found a similar number, about 4.1 million suns, with an uncertainty of plus or minus 600,000 suns. Since this mass is packed into a space only 44 million kilometers wide, it gives a density 10 times higher than earlier estimates. Later studies looked at thousands of stars within about 1 parsec, just over 3 light years, of the black hole. Using statistics, astronomers estimated the black hole's mass at about 3.6 million suns, plus 200,000 and minus 400,000 suns, with another 1 million suns spread nearby. This extra mass probably comes from normal stars and remains of dead stars. Even though it is massive, Sagittarius A star is small for a supermassive black hole, and its weak radio and infrared glow shows that the Milky Way is not an active Seyfert galaxy. It is important to note that what we see is not the black hole itself. It remains invisible, but the glowing gas and dust heated to millions of degrees as they spiral inward. The black hole itself gives off only an incredibly faint Hawking radiation, around 10 to the minus 14 Kelvin, far too weak to detect. More evidence comes from high-energy observations. The European Space Agency's gamma-ray observatory, Integral, saw gamma rays hitting the nearby giant cloud Sagittarius B2, making it glow in X-rays. The total brightness of this event was estimated at about 1.5 times 10 to the 39th ergs per second, 1,000,000 times brighter than Sagittarius A star now, and similar to a typical active galactic nucleus. In 2011, Japanese astronomers using the Suzaku satellite confirmed these results, adding more proof of the black hole's effect. In July of 2019, astronomers reported a star called S5HVS1 moving through space at an amazing 1,755 kilometers per second, or nearly 4 million miles per hour, about 6,000ths the speed of light. This star, in the southern constellation Grus, or the Crane, about 29,000 light-years from Earth, may have been thrown out of the Milky Way after a close encounter with Sagittarius A star, showing the black hole's great gravitational strength. At the center of our Milky Way galaxy lies Sagittarius A, a supermassive black hole full of mysteries. Orbiting very close to it is a group of stars called the S-stars. These stars are remarkable. They move in dizzying paths around the black hole, tracing the invisible pull of a force so strong it bends space and time. Because clouds of cosmic dust block visible light, astronomers study these stars using infrared light, especially in the K-band, which can pass through the dust. The study of the S-stars is changing quickly. In 2011, astronomers mapped the orbits of the main stars at that time, comparing their loops around Sagittarius A to the planets in our solar system. There was excitement when S62 seemed to come closer to the black hole than any star seen before. Later, observations showed that this approach was not as close as first thought. The S-stars are valuable because of their speed and closeness to the black hole. This helps scientists measure the size of Sagittarius A and notice small effects predicted by Einstein's relativity, like the shift of a star's nearest point in its orbit. Researchers also watch for stars that might get too close and be torn apart, but luckily, none are expected to meet that end. As of 2020, the record for the closest approach is held by S4714. This star gets to about 12.6 astronomical units, about 1,880,000,000 kilometers of Sagittarius A. This is nearly the same distance as Saturn from the Sun. S4714 moves at almost 8% of the speed of light. Its orbit takes about 12 years, and it is very stretched out with an eccentricity of 0.985, explaining its close approach and high speed. These numbers have some uncertainty. The closest distance could change by plus or minus 9.3 astronomical units, and its speed by plus or minus 8,840 kilometers per second. Detailed lists exist for the S-star cluster, showing each star's orbit, size, shape, tilt, direction, closest approach times, brightness in infrared, and speed and distance at the nearest point to Sagittarius A. One interesting visitor is the gas cloud G2. First seen in 2002, G2 has a mass about 3 times that of Earth. In 2012, a paper said that G2 was moving toward the black hole's accretion zone, the area where matter spins inward and disappears beyond the event horizon. Predictions said G2 would reach its closest point, or perinigrikon, in early 2014 at just over 3,000 times the black hole's radius, around 260 astronomical units, or about 36 light-hours away. Observations since 2009 showed the cloud slowly being pulled apart. Some scientists thought it might be destroyed, creating bright X-rays and other light. Others believed G2 could hide a faint star or be 2 stars joined together, keeping it whole near the black hole. In the month of May, in the year 2013, scientists proposed a fascinating idea about an unusual object near the center of our galaxy, known as G2. They suggested that before making its closest pass around the supermassive black hole called Sagittarius A star, this mysterious gas cloud might come into close contact with other stars or the strange dense remains of dead stars such as neutron stars that orbit the black hole. If such encounters happened, they could provide scientists with a rare and valuable glimpse into one of the most extreme and violent regions in the Milky Way, the area that lies right next to our galaxy's central black hole. Astronomers around the world were thrilled about the chance to observe G2's journey. The reason for their excitement was simple. Sagittarius A star, despite its enormous size, around 4 million times the mass of our Sun, feeds on matter very slowly. Because it is usually so quiet, even the smallest flickers of activity near it are worth studying. G2's movement offered a kind of natural experiment, a once-in-a-lifetime opportunity to see how a supermassive black hole reacts when a cloud of gas ventures too close to it. Many of the world's most powerful observatories joined forces to monitor this event. Among them were Chandra, XMM Newton, the Very Large Array, Integral, Swift, and Fermi. Additional observing time was also requested for the Very Large Telescope in Chile and the mighty Keck Observatory in Hawaii. At the same time, scientists from the European Southern Observatory and the Lawrence Livermore National Laboratory ran detailed computer simulations to predict what might happen when G2 approached the black hole. Astronomer Darrell Haggard expressed the excitement shared by many researchers when she said, "It's thrilling to have something that feels more like a real experiment," hoping that the event would unlock new secrets about how black holes behave and feed. When the long-awaited closest approach finally took place in March of the year 2014, however, the results were far less dramatic than expected. There were no spectacular outbursts or brilliant flashes of light. Observations made on the 19th and 20th of March showed that G2 was still intact after passing by the black hole. This surprising survival suggested that something solid, possibly a small star hidden at its core, was holding the cloud together against the black hole's enormous tidal forces. A few months later, on the 21st of July 2014, astronomers using the Very Large Telescope in Chile made another surprising discovery. Their observations indicated that G2 might not be a simple cloud of gas after all. Instead, it could be a thick clump within a much larger and thinner stream of gas that slowly spirals towards Sagittarius A star. Rather than causing a sudden bright flare, this stream might be feeding the black hole little by little in a slow and steady process. This idea gained even more support when astronomers noticed something familiar. A similar cloud called G1 had passed close to the black hole about 13 years earlier, following almost the same path through space. Together, these two clouds, along with a faint trailing stream of gas, seemed to form part of a continuous river of matter slowly flowing into the heart of the galaxy. Renowned astronomer Andrea Ghez and her colleagues went a step further. They proposed that G2 might not be just a random blob of gas, but rather the aftermath of a cosmic collision. Perhaps long ago, two stars that once orbited each other closely had crashed together and merged into a single, much larger star, still surrounded by a shell of gas and dust. This bold idea would explain how G2 managed to survive its close encounter with the black hole without being torn apart, a mystery that had puzzled scientists since the beginning.